Right now, somewhere in the world, a physicist is sitting in front of a screen full of equations that describe a moment before time itself began. The equations should not work. By every rule of ordinary physics, the question they are trying to answer should be meaningless. And yet the math keeps speaking. It keeps pointing to something. It keeps suggesting that the Big Bang, the event we have been taught was the beginning of everything, may not have been a beginning at all. For most of the last century, science treated the Big Bang as a wall. Behind it, the universe we know, with its galaxies and stars and laws of physics. In front of it, nothing. Not empty space, not darkness, but the absence of before itself. To ask what came before the Big Bang was considered a kind of category mistake, like asking what is north of the North Pole. The question simply had no meaning. That has begun to change. In the last few decades, serious cosmologists, Roger Penrose, Stephen Hawking, Paul Steinhardt, Neil Turok, Alexander Vilenkin, Andrei Linde, and many others, have proposed a set of mathematical models that look behind the wall. None of them have been proven, none of them may ever be, but each one suggests that the Big Bang was not a beginning, only a transition, from something into something else, and what they describe when you read it slowly and let it sink in is genuinely unsettling. Tonight we'll move slowly through these ideas, through the best science has to offer about what may have existed before the first moment of time. We will be honest about what we know, what we don't, and what we may never know. Some of it is beautiful, some of it is disturbing. All of it sits on the very edge of what minds like ours are equipped to understand. If you find this kind of slow, careful exploration helpful, consider hitting like and subscribing. It quietly helps more than you might think. For thousands of years, the question of what came before everything was the province of religion and philosophy, not of science. It was simply too large, too remote, too strange to be touched by the measurement. You could think about it, argue about it, build belief systems around it, but you could not study it. The beginning of the universe lay beyond any possible observation, hidden by an unbridgeable gulf of time. Whatever was there in the deepest past was not something a microscope or a telescope could ever reach. This is what made the question feel almost forbidden. To ask what existed before the universe was to step out of science and into something else. It was a question without a method, a question that no experiment could ever settle. And so for most of history, even thoughtful people simply set it aside. They acknowledged it as the deepest question, accepted that it had no scientific answer, and moved on to questions they could actually investigate. The origin of everything was treated as a closed door behind which lay only mystery. What has changed in our lifetime is remarkable. Through a combination of new physics, new observations, and new mathematical tools, scientists have begun to push against the closed door. They have not opened it. They may never open it. But they have started, for the first time, to ask the question in a way that is not purely speculative, to bring it inside the boundaries of mathematics, where ideas can be tested against one another, where consequences can be derived, where some hypotheses can be ruled out and others left standing. The question that was supposed to be unanswerable has become slowly and carefully a question that can at least be examined. This shift is one of the strangest developments in the history of science. The deepest question of all, what came before the beginning, was thought to be permanently beyond reach, and now it is being explored tentatively by serious researchers using serious mathematics. They are not pretending to have answers. None of them claims to know what truly happened before the Big Bang. But they are doing something that would have seemed impossible only a few generations ago. They are making the question into a scientific one, with proposals that have specific consequences, some of which we may someday be able to test. The reason for this shift is not that we have suddenly become wiser. It is that the question itself has been transformed by our understanding of what the Big Bang actually was. For a long time, the Big Bang was pictured as a fixed wall, an absolute beginning before which there was nothing to discuss. But as cosmology has developed, that picture has cracked. The wall has become less of a wall and more of a horizon, a place where our current understanding breaks down, rather than where existence itself begins. And once you have a horizon instead of a wall, you can at least try to imagine what might lie beyond it. There is something humbling and also a little terrifying in this. Humbling because we have to admit that the simple story, the universe began with a bang and that, was always a simplification, a placeholder for our ignorance. Terrifying because what lies beyond that placeholder may be far stranger and far more unsettling than the simple story suggested. The hypotheses we will examine on this journey are not comforting. Some of them imply that the universe has no beginning at all. Some imply that before is a meaningless word. Some imply that everything that has ever happened to you has happened and will happen, an infinite number of times. None of them is easy. It's worth pausing here to acknowledge how strange the modern situation really is. For all of human history before the last few decades, the question of cosmic origins was answered, when it was answered at all, by stories, creation myths, theological frameworks, philosophical speculations. These stories served real purposes. They gave people a sense of orientation in a universe too large to grasp directly. What is happening now is something genuinely new. Stories are being replaced not by other stories but by mathematical proposals, equations whose consequences can be followed, predictions whose signatures might one day be detected, hypotheses that disagree with each other in precise and testable ways. The deepest question is no longer the property of mythmakers. It has become, however, incompletely a problem for science. So we begin here with a question that should not have an answer, and that is starting, barely carefully, to be approached as if it might. We will not pretend that science has solved the deepest mystery. It has not, and it may never, but it has begun to look behind the wall, and what it has seen there is worth understanding, even if it disturbs us. To begin, we have to understand exactly what the Big Bang was and was not. Because the popular picture of the Big Bang, the one most people carry in their heads, turns out to be wrong in ways that change everything. Before we can ask what came before the Big Bang, we have to be honest about what the Big Bang itself actually was. Because the picture most people carry of it, and the picture that popular science often hands us, is misleading in important ways. When you correct the picture, the question of before changes shape entirely. It stops being a question about an explosion in space and becomes something far stranger and more unsettling. The popular image is of an enormous explosion in empty space. A point of immense energy detonates, and matter flies outward into a pre-existing void, filling it with stars and galaxies over billions of years. The Big Bang in this picture was an event in space, a kind of cosmic firework, lighting up a stage that already existed. From this picture, the question what came before the Big Bang feels natural. The stage was there, the explosion was there, so what was happening on the stage before the explosion started? This picture is wrong in almost every detail. The Big Bang was not an explosion in space. It was, according to the best theories we have, an expansion of space itself. Space did not pre-exist the Big Bang as an empty stage waiting to be filled. Space itself came into being with the Big Bang, or was at least transformed from some other state into the expanding cosmos we observe today. Time, too, may have begun with the Big Bang. In the standard interpretation of Einstein's equations, asking what came before is like asking what is to the south of the South Pole. There is no direction further south, because south runs out at the pole itself. This is why, for most of the 20th century, serious physicists treated the question of before as a non-question. If time itself began with the Big Bang, then there was no before. The word lost its meaning at the boundary. The universe was not preceded by something else. It simply was, starting at the first instant, with no prior moment to speak of. This was not a refusal to think about the question. It was a careful mathematical conclusion drawn from the best theory of space and time we had. And for a long time that seemed to be the end of the matter. But notice what this picture really says. It does not say that nothing existed before the Big Bang. It says that the word before does not apply. These are very different claims. One asserts a state of pre-existing nothingness. The other says the question is malformed. And both of these are themselves answers, of a kind answers that we may have outgrown. Because in recent decades, physicists have started to wonder whether the assumption that time strictly began with the Big Bang might be too strong, whether it might be a simplification that breaks down when we look more carefully, whether the wall might have something beyond it after all. What changed was the recognition that the Big Bang itself, the very first moment, the singularity where everything was infinitely dense and infinitely hot, is not actually described by our current theories. It is described by a mathematical extrapolation that breaks down at the singularity. The math says infinity at that point. And infinity in physics is almost always a sign that something has gone wrong with the theory, not that something infinite is real in the world. So the singularity, the supposed starting line of everything, may not be a real starting line at all. It may be a place where our current theory simply stops working, and a deeper theory would tell us what really happened there. This is a profound shift and is worth dwelling on. If the singularity is not a real beginning, but a sign of an incomplete theory, then everything we thought we knew about the wall of the Big Bang has to be revisited. The wall might not be a wall. It might be a fog, beyond which there is more universe we have not yet been able to describe. and the question of what came before the Big Bang stops being a category mistake and becomes a real question about a real region of existence which we are simply not yet equipped to study. So the Big Bang was not an explosion in empty space, and time may or may not have truly begun with it. The popular picture has misled us in important ways, and the real story is stranger. To go further, we have to look directly at the singularity, the moment of supposed infinite density and infinite heat, and understand why it is almost certainly not what it appears to be. Because the singularity is the doorway, the place where the next step in this journey begins, and the doorway, when examined carefully, turns out not to be solid. We have just seen that the moment of the Big Bang itself is described, in our current theories, by something called a singularity, a single point of infinite density and infinite temperature from which the entire universe expanded outward. The word singularity sounds technical, almost reassuring, as if it names something definite. But when you look closely at what the singularity actually is, you find something very strange. It is the place where physics, as we know it, completely breaks down. It is not a thing we understand, it is a sign that we don't. In ordinary physics, when an equation gives you the answer infinity, that is usually a warning. It is telling you that the theory has been pushed past its limits, into a region where it stops making sense. If you try to calculate the temperature of a fire and your math returns infinite temperature, you do not conclude that the fire is infinitely hot. You conclude that you made a wrong assumption somewhere, that your model is too simple, that something you have not yet understood is intervening. Infinity, in physics, is almost always a sign that your theory has reached the edge of its validity. It is not a description of reality, it is a description of where your description fails. The singularity at the start of the universe is exactly this kind of infinity. When we run the equations of general relativity backward in time, tracing the expansion of the universe back to its earliest moments, we find that the matter and energy of everything pile up tighter and hotter and more compressed, until at the very first instant the density and temperature go to infinity. This is the singularity, and it is not a real physical thing. It is the point at which general relativity, our best theory of gravity, simply stops being able to describe what is happening. The theory is shouting in its own language, "I do not know what to say here." This is a crucial realization, because for a long time the singularity was treated almost as a real object, a literal beginning, an absolute starting line of everything. But most working cosmologists today agree that the singularity is almost certainly not real. It is an artifact of an incomplete theory. The real universe, at that earliest moment, did something, but what it did is not described by the equations we currently have. To understand the true earliest moment, we would need a theory that does not break down where general relativity does. We would need a theory of quantum gravity, a theory that combines our understanding of the very large, gravity, space-time, with our understanding of the very small, quantum mechanics. We do not yet have such a theory. We have candidates, string theory, loop quantum gravity, causal sets, and several others, each of which tries to extend physics into the region where general relativity fails. Each of them has different ideas about what really happens at the would-be singularity. And here's the remarkable thing, in almost every one of these candidate theories, the singularity disappears. It is replaced by something else, not an infinite point, but a finite, smooth transition. The beginning turns out, in these theories, to be not an end of all befores, but a region where the universe was in some other state before becoming what it is now. This is one of the most important and least appreciated facts in modern cosmology. The singularity, the supposed beginning of everything, is almost certainly not a real beginning at all. It is a placeholder, a sign of an unfinished theory. And once you remove the singularity from your picture of the early universe, the question what came before stops being meaningless. It becomes the question of what state the universe was in before the moment our current theories can describe. That is a question with real possible answers, answers we will spend the rest of this journey exploring. So when you hear someone say that the universe began with a singularity, you should hear it not as a statement about reality, but as a confession about our current understanding. We do not know how the universe truly began. We know how it looked when our equations could still handle the math, and we know that running those equations all the way back gives a meaningless infinity. What lies on the other side of that infinity, in the real universe, not in the broken equations, is one of the deepest questions science is now beginning to approach. And to approach it, we first have to step back and look at how close to the singularity we can actually see. The answer is closer than you might think. and also in another sense frustratingly far, because while we cannot peer behind the singularity, we can peer to within an absurdly small fraction of a second after it, close enough that the universe was almost beyond imagination. And in that first sliver of time, the strangest things in physics happened. To get our bearings, we need to look at that first trillionth of a second now. When cosmologists talk about how close we can see to the beginning, they are talking about how close to the singularity our current theories can still describe what was happening. The answer is genuinely astonishing. We can describe with confidence the state of the universe to within tiny fractions of a single second after the Big Bang, fractions so small that they require numbers with many zeros after the decimal point. And within that first sliver of time, the universe went through a series of stages so extreme that they make the rest of cosmic history look almost calm by comparison. Let us be honest about the scales involved. The first second after the Big Bang is by ordinary standards almost no time at all, but for the universe that first second was a whole epoch, divided into many distinct phases, each lasting a tiny fraction of the second. Within the first trillionth of a trillionth of a trillionth of a second, written as a decimal point followed by many zeros, the universe is thought to have undergone a process called cosmic inflation, in which it expanded faster than the speed of light, growing from a region far smaller than an atom to something macroscopic in an unimaginably brief instant. This was not the Big Bang as commonly pictured. It was something that happened immediately after, in the very first sliver of time. Then, after inflation ended, the universe was a hot, dense soup of fundamental particles, far too hot for atoms to exist. As it expanded and cooled over the next fraction of a second, the forces of nature separated out, particles condensed from energy, and the basic ingredients of matter began to assemble. By the time the universe was a single second old, it already had the basic furniture we recognize today: protons, neutrons, electrons, photons, all in a hot, dense plasma, still too energetic for ordinary atoms to form. The cosmos at 1 second old was already past most of its most extreme phases. The drama of the first second was already over. What is remarkable is that we can describe most of this. The physics from somewhere around 1/10,000th of a second onward is well understood. We have particle accelerators that can reach those energies, and the math works. Even the earlier phases, up to a tiny fraction of a second after the supposed beginning, can be described with confidence using theories we have tested in other contexts. The first second of the universe is, in many ways, the best documented second in cosmic history, in the sense that we know an enormous amount about what was happening in it, even though we cannot directly observe it, but there is a limit. As we push further back, the energies and densities grow until they exceed anything we can test in a laboratory. Eventually we reach the so-called Planck era, the earliest fraction of a second, when the universe was so hot and dense that quantum gravity becomes essential. This is roughly the boundary at which our current theories give out. Before this, we cannot say with any confidence what was happening, because our equations stop being reliable. The Planck era is not a wall exactly, it is more like a fog, beyond which our current vision fails, and the singularity, if there was one, lies on the other side of that fog. So the closest we can see with present physics is the first tiny fraction of a second after the moment we call the Big Bang. We can describe almost everything that happened from then onward, but not the moment itself, and not anything that might have been before. And here is where the disturbing realization sets in. We are not asking what was before the Big Bang from a position of ignorance, hoping for any answer. We are asking it from a position of having almost everything else mapped out. The entire history of the universe for 13.8 billion years is reasonably well understood. There is just this one stubborn region at the very beginning that lies behind our current vision, and it is precisely that region where the deepest mysteries hide. What is in that region? Was there a true beginning? Or did the universe transition from some earlier state? Did time start there, or was there something we could call before? These are the questions we are now equipped to ask. They are not philosophical questions anymore, or at least not only. They are questions about a specific finite region of cosmic history, the region just before the limits of our current theories. And the answers, whatever they are, must be there, written in physics we do not yet fully understand. Cosmologists are beginning to peer at that region, even if only by reasoning and mathematics rather than direct observation. And to do that, they have had to confront the question of how far back we can ever see, not in theory, but in the actual fossil light of the universe itself. When we look out at the universe with our telescopes, we are looking back in time. Every point of light is older than itself, carrying its image to us across the gulf of years. The farther we look, the further back in time we see. So in principle, looking deep into space should let us look deep into the past. And it does, up to a point. But there is a wall, a literal, observable wall, beyond which our telescopes cannot see. It is the oldest light in the universe, and it marks a boundary that no observation can ever penetrate further. To understand the question of before, we have to understand this wall, because everything we want to ask about lies on the other side of it. The wall is called the cosmic microwave background, or CMB. It is a faint, almost uniform glow of microwave radiation, coming from every direction in the sky, detectable by sensitive radio telescopes and satellites. It is the oldest light in the universe, light that was released about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form for the first time. Before that moment, the universe was so hot and dense that light could not travel freely. Photons were constantly absorbed and scattered by the soup of charged particles filling space. The cosmos was opaque, like the inside of a thick fog. Then, at around 380,000 years, the universe cooled to the point where atoms could finally form and the fog cleared. Light, freed at last, streamed outward in all directions, carrying with it the imprint of the conditions at that moment. That light has been travelling ever since, stretched and dimmed by the expansion of the universe, until now it reaches us as the faint microwave glow of the cosmic background. When you tune an old analog television to an empty channel, a small fraction of the static you see is this primordial radiation, the afterglow of the early universe reaching your screen. The CMB is the wall. It is the farthest back in time we can see with light. Anything that happened before the CMB was emitted is hidden behind the fog. We cannot see through it with telescopes, no matter how powerful. The CMB shows us the universe at 380,000 years old. Before that, the universe is invisible to direct observation, and remember, the Big Bang itself, whatever it was, happened about 380,000 years before the CMB was released. So the entire first 380,000 years of cosmic history, and certainly anything that came before that, is hidden from our direct view by this wall of fog. This is a profound and somewhat humbling fact. We have built incredible telescopes that can see almost back to the moment when atoms formed. But we cannot see further. The information about the very early universe, the Planck era, the inflationary period, the supposed singularity and anything before is not directly visible. It is locked behind the cosmic fog. To learn about it, we have to be clever. We have to look for subtle imprints, faint signatures, indirect clues, features in the CMB itself that may have been shaped by what happened earlier, or other phenomena like gravitational waves that might carry information from before the fog cleared. This is the heart of the difficulty in answering our question. Whatever happened in the first moments, and certainly whatever came before, left at most faint traces in the cosmic background, in the distribution of matter, in the patterns of structure across the sky. Cosmologists are working hard to read these traces, but it is delicate work, and the signals are subtle. We are like detectives trying to reconstruct an event from a single faint footprint and a few scattered hairs. We can do astonishing work with little, but we are nowhere near being able to directly see what happened in those earliest moments. The wall stands, and we work around it. And yet, there is one more thing to understand about this wall, which makes the whole situation even stranger. When we look at the CMB, we are looking at the sky from every direction at once, and the CMB looks almost identical no matter where we look. The temperature of this early universe was extraordinarily uniform across vast distances, far more uniform than any process within the universe should have been able to produce. This uniformity is itself a puzzle, and the standard solution, cosmic inflation, an exclusive expansion in the first sliver of a second, is one of the most powerful and important ideas in modern cosmology. It is also, as we will see, one of the most important reasons to suspect that the Big Bang was not really the beginning at all. Before we move into the actual scientific theories about what came before the Big Bang, we have to sit with a deep difficulty, a difficulty that is not technical but conceptual, and that may turn out to be the most disturbing aspect of the whole investigation. The word before is so familiar, so ordinary, that we use it without thinking. Before lunch, before the war, before the Big Bang. But in physics, before has a very specific meaning, and that meaning may not survive at the boundaries of our universe. The question what came before the Big Bang may turn out, on careful examination, to be a question that simply cannot be asked. Before is a relationship in time. It means earlier than, prior to. It assumes that time exists flowing from past to future, with each moment having an unambiguous earlier and later. In ordinary life, this is so obvious it is invisible. We live inside time. We cannot imagine being outside it. Time is the medium in which our experience unfolds, the framework on which everything else is hung. The idea of something happening outside of time or before time existed is almost impossible for the human mind to picture. We try and we find ourselves picturing it as taking place in some other kind of time, a meta-time within which our own time started. But that just pushes the question back. In Einstein's theory of general relativity, time is not a fixed background. It is part of the fabric of the universe, woven together with space into a single thing called space-time. And like space, it can be curved, stretched and shaped by the matter and energy within it. When we run the equations of general relativity backward toward the Big Bang, we find that time itself becomes part of what is curving and shrinking. At the singularity, time as we know it does not just stop, it ceases to be a coherent concept at all. It is not that there was a moment before and another moment after the beginning. There was no before, because time itself was not in existence in the form we understand it. The famous comparison, often associated with Stephen Hawking, is to the South Pole. If you stand at the South Pole and ask, "What is south of here?" the question has no answer, not because the answer is mysterious, but because south simply runs out at the pole. There is no direction further south. The question is malformed. It presupposes something that does not exist. In the same way, the question what came before the Big Bang may presuppose a before that does not exist. The Big Bang may not be an event in time with a prior moment. It may be the boundary of time itself, beyond which the word before has no meaning. If this is right, then the answer to our question, what came before the Big Bang, is strictly nothing came before, not because there was a state of nothingness, but because there was no before to be a state of anything. This is not nothing in the everyday sense. It is a deeper kind of unanswerability, in which the question itself fails before any answer can be given. And this is one possible position, defended seriously by many physicists, including Hawking himself for much of his career. But, and this is where things become interesting, this position assumes that general relativity gives the correct description of time at the earliest moments, and as we have already seen, general relativity breaks down at the singularity. So the conclusion that time itself began with the Big Bang is, like the singularity, a conclusion drawn from a theory at its limits. Maybe time did begin with the Big Bang, or maybe time, like the singularity, is described differently in a more complete theory. And what we call the beginning is really a transition from some earlier state of time, or from some state in which something time-like, but not quite time as we know it, was already going on. So we live with two possibilities, and we cannot yet choose between them. Either before the Big Bang is a meaningless phrase because time itself began there, and the question is malformed. Or time existed in some form before the Big Bang, and there was a state of the world, a state we are at the very edge of being able to think about. Both possibilities are unsettling in their own ways. The first because it forces us to accept that the deepest question may have no answer, not because we are too small, but because the question is broken. The second because it implies that the universe has a hidden past, a stretch of existence preceding everything we know, of which we are profoundly ignorant. We will return to this difficulty throughout the journey. For now, hold it in mind as a kind of warning sign. Whenever we say before the Big Bang, we may be using a word that does not really apply, that survives only as a habit of speech. The honest cosmologist has to constantly check whether before still means anything in the context of a given theory. Some theories preserve a meaningful before, some do not. And to begin to see why this question has not been simply abandoned, we should turn to the way thinkers have wrestled with it for far longer than there has been any science, because the question itself is ancient, and its ancient versions still echo in our modern attempts. The question of what came before the universe is not new. It is one of the oldest questions humans have ever asked. Long before modern cosmology, before telescopes, before the Big Bang theory was even imagined, thoughtful people sat under the night sky and wondered the same thing we are wondering tonight. Was there ever a beginning? And if so, what was there before? The way they answered tells us something important about how strange the modern question really is, because some of them anticipated 16 centuries ago, the very puzzle that physicists are wrestling with now. In the late 4th century, a North African theologian named Augustine of Hippo wrestled with what he called the question of before. In his own framework, the universe was created by God at a specific moment in the past. Naturally, people ask the obvious question: what was God doing before that moment? What occupied the infinite time before the universe came into being? Augustine recognized that the question, framed this way, led to an absurdity. If God had existed for an infinite time before creating the universe, why this moment and not another? And what would it even mean for time to stretch backward forever, with nothing happening? His answer was as elegant as it was radical. Time, Augustine argued, was itself part of creation. It was not a pre-existing stage on which events were arranged. It was woven into the fabric of the world that came into being. Before that creation there was no before, because time itself did not exist. The question what was happening before the universe began was therefore not a meaningful question. It assumed a time outside of time, which is a contradiction. The universe did not begin within a pre-existing stretch of time. Time and the universe began together. This is, almost word for word, the position that Stephen Hawking and many modern cosmologists would defend more than 1500 years later. The insight that time may be part of the universe rather than its background survived from theology into physics, taking on new precision but keeping the same essential shape. When Hawking compared asking what is before the Big Bang to asking what is north of the North Pole, he was reaching back, knowingly or not, to a tradition Augustine had helped found. The question is malformed because the concept of before runs out at the boundary, just as north runs out at the pole. There is no further direction in which to look. There is something humbling and remarkable in this continuity. 16 centuries apart, in radically different intellectual worlds, thoughtful people reached the same conclusion, that the deepest question about the origin of everything may be malformed in a particular way. The conclusion is the same, only the language and the tools differ. Augustine was working with theology and philosophy. Hawking was working with general relativity and quantum mechanics, but they arrived at strikingly similar places, and both, it turns out, may have been right in part and wrong in part, because the modern question has not stayed where Augustine left it. It has moved on in ways that he could not have anticipated. What has changed since Augustine is that we now have specific mathematical theories of how time and space behave at the most extreme conditions. We can ask precisely what the theory predicts at the boundary, and we can notice when the theory breaks down. And as we have seen, our current theories do break down at the supposed beginning. So the Augustinian answer, that before is a meaningless word, depends on whether the breaking down theory or some deeper theory is the true picture. If general relativity is the final word, then Augustine's answer holds: there is no before, and the question has no meaning. If general relativity is replaced at the smallest scales by quantum gravity, then maybe there is a before, after all. Just one our current theories cannot describe. This is the crux of the modern situation. The question Augustine resolved philosophically remains open scientifically, because we do not yet know which theory describes the earliest moments, and so the answer, there was no before, is one possibility among several. It is no longer the obvious answer. It is one hypothesis competing with others, each of which has its own kind of mathematics, its own kind of evidence, its own kind of strangeness. The question that was supposed to be closed has been reopened, by physics rather than by philosophy, and now there are several different ways to think about it. Some of them keep the universe finite in age, others stretch it backward forever. All of them are strange, so the question is 16 centuries old in its modern shape, and far older in its ancient ones. What is new is not the question, but the tools we have to try to answer it. And the first of those tools, the one that broke open the modern investigation, is a strange idea about the very first sliver of cosmic time. An idea that, almost as a byproduct, suggested for the first time that the Big Bang might not have been the true beginning. That idea is called cosmic inflation, and once you understand what it implies, the wall behind the Big Bang starts to crack. The first serious crack in the picture of the Big Bang as the absolute beginning came from a theory that was not originally designed to address the question of before at all. It was designed to solve a different puzzle, a strange uniformity in the cosmic microwave background that should not have been there. The theory is called cosmic inflation, and once you understand what it proposes, you begin to see why some cosmologists now suspect that the Big Bang was not the start of the universe but a stage in a much longer, possibly endless, story. The puzzle was this. When we look at the cosmic microwave background, that wall of oldest light from when the universe was 380,000 years old, we find that its temperature is extraordinarily uniform across the entire sky. Different patches of the sky, separated by enormous distances, show almost exactly the same temperature, to within tiny fractions of a degree. This uniformity is so precise that it cannot be explained by ordinary physics. Distant patches of the sky have never been in contact with one another. Not even light has had time to travel between them since the Big Bang. So how did they end up at the same temperature, as if they had once been in equilibrium? In the early 1980s, the physicist Alan Guth proposed a startling solution. Suppose that in the very first instant of the universe, within the first tiny fraction of a second, there was a brief period of incredibly rapid expansion. Not the steady expansion we see today, but an exponential blow-up, in which a tiny region of space was stretched, in an unimaginably short time, into something vastly larger. During this period, called inflation, the universe expanded faster than the speed of light, growing from something smaller than an atom to something macroscopic almost instantly. After inflation ended, the universe entered the more leisurely expansion we have observed ever since. This solved the uniformity puzzle elegantly. Before inflation, the part of the universe that would become our observable cosmos was a tiny region, small enough that it had already reached thermal equilibrium, every part of it the same temperature, naturally, because the parts could exchange heat. Inflation then stretched this small uniform region to enormous size, carrying the uniformity along with it. The patches of the sky that look identical to us today were once in close contact, far back before inflation. They only became distant because of the inflation itself. The uniformity is a relic of a time when everything was tiny and connected. Inflation is one of the most successful ideas in modern cosmology. It explains not only the uniformity but several other features of the universe that would otherwise be deeply puzzling. It predicts correctly the tiny variations in the cosmic background, variations that would later grow into galaxies and clusters in the cosmic web. It's supported by multiple lines of evidence, and most cosmologists today consider it part of the standard picture of the early universe, even though some details remain debated. But here is where things become interesting. Inflation, as a theory, requires a kind of pre-Big Bang state. It does not start from a singularity. It starts from a small patch of space, already in a particular condition, filled with a special kind of energy that drives the exponential expansion. This energy, often called the inflaton field, has to be there from the start. And the question naturally arises, where did the inflaton field come from? What was the universe like before inflation began? Was there a state of the cosmos preceding the inflationary burst? In the simplest versions of inflation, this question is left somewhat open. The inflationary phase replaces the singular beginning of the universe with a smoother, more controllable picture. The Big Bang in this view is not a singular point but the end of inflation, the moment when the inflaton field released its energy and gave rise to the hot, dense soup of particles that we have always associated with the early universe. The Big Bang becomes a stage in a longer process, and what came before that stage, what gave rise to inflation in the first place, becomes a serious scientific question, not a metaphysical one. This is the first crack. Inflation, by replacing the singularity with a smoother story, opens the door to asking what was happening in the universe just before our observable cosmos came into being. It does not, by itself, give a definitive answer, but it shows that the beginning we used to think was an absolute wall can be pushed back into a region where physics still applies, where there is still mathematics to do, where there may still be a before worth investigating. And once you have made that move, an even more radical possibility opens up, because the theory of inflation taken seriously suggests that inflation may never have truly begun at all, that it may stretch backward without limit. And that idea, called eternal inflation, changes everything. Inflation, once it takes hold in a region of space, has an unsettling property. Under the most natural assumptions of the theory, it does not stop everywhere at once. Most of the inflaton field eventually decays, releasing its energy and producing the hot Big Bang we observe. But in some regions, quantum effects keep the inflaton field aloft a little longer, and those regions go on inflating. Then within those still inflating regions, more subregions stop inflating and become Big Bangs of their own, while still other subregions go on inflating, generating still more pocket universes. The process, once started, never fully stops. This is called eternal inflation, and its implications are staggering. Eternal inflation was proposed and developed in the 1980s by physicists including Andrei Linde, Alan Guth, and Alexander Vilenkin. It is not a fringe idea. It is a natural consequence of taking inflation theory seriously and applying quantum mechanics carefully to the inflaton field. In most versions of inflation, eternal inflation appears almost automatically. The math says, inflation, once it begins, continues forever in the larger picture, spawning an endless cascade of pocket universes, each one a big bang from the perspective of its inhabitants, but each one really just a localized end of inflation within an ever-inflating greater whole. Stop and consider what this implies for our question. If eternal inflation is correct, then our Big Bang, the event we have been thinking of as the beginning of our universe, is not the beginning of anything fundamental. It's one of many transitions from inflating space to non-inflating space, one of countless local exits from the inflationary state. Our entire observable universe, with its 2 trillion galaxies and its 13.8 billion years of history, is a single bubble in a vastly larger structure of eternally inflating space in which other bubbles, other Big Bangs, are constantly being born. And here is the disturbing part. If inflation is eternal in the forward direction, going on forever into the future, generating new bubbles without end, then the process may have no beginning in the past either. There may have always been inflation. The eternal inflationary state may stretch backward as well as forward, an infinite cascade in both directions, with no first moment. Some versions of the theory require a beginning to inflation, while others suggest it may have existed forever. In the latter versions, the universe, meaning the whole inflationary structure, not just our bubble, has no beginning at all. It simply is eternally, infinitely, with bubbles like ours appearing within it constantly throughout an unbounded past and future. If this is right, then the Big Bang was not the beginning of the universe. It was the beginning of our universe, our local bubble, but not of the larger reality that contains us. Before our Big Bang, in this picture, there was an inflating region, endless, vast, in which the seeds of our cosmos were quietly multiplying. And before that, more of the same. And before that, more. There is no first event, no original spark, no point at which everything began. There is only the eternal inflationary state going on forever, producing universe after universe in its endless stretching. This is one of the most well-developed scientific proposals for what came before the Big Bang. It is not science fiction. It's what falls out of the equations when you take inflation seriously and apply quantum mechanics carefully. Most leading cosmologists consider eternal inflation a serious possibility, and many think it is likely. It is not proven, none of these pre-Big Bang theories are, but it is grounded in the same mathematics that has produced our current, highly successful picture of the early universe. The same theory that explains the uniformity of the cosmic background may also imply that our universe is just one bubble in an eternally inflating multiverse. The implications are difficult to absorb. Eternal inflation does not just answer the question what came before the Big Bang, it dissolves the question. There was no single Big Bang, there were and are countless Big Bangs, scattered through an eternally inflating substrate. There is no beginning to look for. The universe, in the largest sense, has always existed, in the form of an endlessly inflating space that occasionally spawns pocket cosmoses like ours. Our Big Bang is just one moment in a vastly larger story that has no first chapter. And once you accept this picture, an even stranger consequence follows. If inflation eternally produces new universes, and has been doing so forever, then the number of universes is infinite. Each pocket universe has its own physics, its own initial conditions, its own laws emerging from the way inflation happened to end in that region. Some universes are like ours, some are very different. And in an infinite multiverse, all the possibilities are realized somewhere. This is where the disturbing implications truly begin to bite. Because if there are infinite universes, there are infinite copies of you, and infinite versions of every life you might have lived. The eternal inflationary multiverse is one of the most unsettling ideas in modern physics, and its disturbing logic is worth confronting directly. Eternal inflation, taken seriously, implies a multiverse. Not a multiverse as a poetic flourish or a science fiction conceit, but a multiverse as a mathematical consequence of taking certain well-tested physics seriously and following where the equations lead. If inflation is eternal, the number of pocket universes is not finite. It grows without bound. And in many models, it is already infinite. And in an infinite multiverse, the consequences for what is possible and what is somewhere actually happening are difficult to absorb without flinching. The basic logic is straightforward. In eternal inflation, regions of space are constantly exiting the inflationary state and becoming new universes. The process has gone on forever, in many versions of the theory, and will continue forever. The total number of pocket universes generated is infinite. Each of these universes starts with slightly different conditions, different distributions of matter, possibly even different versions of physical laws emerging from how inflation ended in that region. The result is not just many universes, but a vast space of possible universes, with most of the variations being realized somewhere in the multiverse. This is sometimes called the inflationary multiverse, or the bubble multiverse, and it is not the only kind of multiverse that physicists have considered. String theory, for example, suggests its own version of a multiverse, in which different regions of the larger reality have different vacuum states and therefore different effective laws of physics. Quantum mechanics, in some interpretations, implies its own multiverse, the many worlds interpretation, in which every quantum event branches the universe into multiple outcomes. These are different ideas, and they may or may not be correct, but they all share a common feature. They all suggest that what we call the universe is not all there is. Now, multiverses are not, in themselves, a settled scientific fact. They are predictions of certain theories that are themselves not fully confirmed. Some physicists are enthusiastic about the multiverse as the natural outcome of our best ideas. Others are skeptical, worried that a multiverse is unfalsifiable, and therefore not properly scientific. The debate is ongoing, and we should not pretend it is settled. But here is the key point. The multiverse is not an exotic philosophical add-on. It is what falls out of equations that we have good reasons to take seriously. If inflation is right, and inflation is eternal, then a multiverse is a consequence whether we like it or not, and the consequences are strange. In an infinite multiverse, every possible variation of physical conditions is realized in some pocket universe. There are universes where the laws of physics are slightly different, universes where the constants of nature have different values, universes where stars cannot form because the physics does not allow it, universes where life is impossible, and importantly, universes where conditions are similar enough to ours that stars and planets and life can arise, and where, in the infinite span of such universes, virtually every possible variation of a human life plays out. This is where the disturbing implication becomes vivid. If the multiverse is infinite, and if pocket universes like ours arise in it with anything more than vanishing frequency, then somewhere, far beyond any horizon we could ever cross, there are other universes containing other versions of you. Versions who made different choices, versions whose lives took different paths. Versions identical to you down to the last atom of your body, because in an infinite ensemble, every possible arrangement of atoms occurs somewhere. The math, applied carelessly, suggests that you exist not once but an infinite number of times scattered across the multiverse, in every possible variation. We will return to this disturbing consequence in the next section because it deserves to be felt slowly. For now, hold it in mind. The equations of inflation, applied without flinching, imply not a single universe but a possibly infinite one, in which our Big Bang was one of countless similar events, and in which we are not unique. Many physicists find this implication uncomfortable. Some try to argue their way out of it, refining the theories to avoid the multiverse. Others embrace it, accepting that the universe is far stranger than common sense suggested. None of them, however, can simply ignore it. Once you take inflation seriously, the multiverse comes along for the ride. So eternal inflation answers the question of what came before the Big Bang in a particular way. There were and are infinitely many Big Bangs scattered through an eternally inflating substrate with no first moment and no beginning. Our universe is one of countless pocket universes, each with its own history. The Big Bang of our cosmos was not the start of all things, only of one bubble among infinite others. And what this means for us, for our sense of identity and uniqueness, is one of the most genuinely unsettling ideas in modern science, and one we have to look at directly before we move on. If the multiverse implied by eternal inflation is real, and if it is truly infinite, then there is a consequence that follows from straightforward mathematical reasoning. It is a consequence that physicists rarely emphasize, because it sounds outlandish, almost like fantasy. but it follows directly from the assumption that the multiverse is infinite and contains universes like ours. The consequence is this: somewhere far beyond any horizon we can ever cross, there exist other copies of you, not metaphorically but literally identical down to the last atom. And there are infinite such copies, leading infinite variations of your life. The reasoning is uncomfortable but inescapable. Take an arrangement of atoms, say, the precise arrangement that makes up you, right now in this moment, with all your memories and thoughts and the specific configuration of your body. This is a particular pattern, complex but finite. Given any region of space large enough to hold a person, there is a finite number of possible arrangements of atoms within it. The number is enormous, almost beyond comprehension, but it is finite. And in an infinite multiverse with infinite pocket universes, the same finite arrangements must recur an infinite number of times. Probability requires it. If you flip a coin infinitely many times, every possible finite sequence eventually appears, infinitely often. The same applies to arrangements of atoms. So in an infinite multiverse, there are infinite copies of you. Some of them are reading these very words at this very moment, in pocket universes physically very similar to ours. Some are slightly different. A copy of you who made one different choice at a crossroads, a copy whose hair is parted on the other side, a copy who never met the people you have met. Across the infinite multiverse, every possible variation of your life is being lived by an exact or near exact copy of you, somewhere out there, beyond any horizon you can ever cross. The mathematics insists on it. If the multiverse is truly infinite and your particular arrangement is possible at all, sit with that because it is strange. It is one thing to feel small against the size of the universe, against 2 trillion galaxies and 13 billion years. It is another thing to learn that the very thing that makes you you, your particular configuration of memories and choices and atoms, is not unique. That you are one instance of a pattern that occurs, in identical and varied forms, an infinite number of times. The feeling this produces is not quite cosmic insignificance. It is more like cosmic redundancy, a sense that whatever you do has already been done, is being done now, and will be done again, infinitely, by versions of yourself you can never meet. This is what some physicists, including Max Tegmark, have called the disturbing implication of the multiverse. It is not science fiction, it is what the math says, if the math is taken at face value and the multiverse is infinite. It is also, importantly, untestable. We cannot reach the other pocket universes. They are beyond every horizon, separated from us by inflating space that no signal could ever cross. The infinite copies of you are mathematically implied but observationally inaccessible. They might exist in the most literal sense, and we would never be able to confirm or deny it. They are real and forever beyond our reach. There is a way to soften this implication, and it is worth mentioning. If the multiverse is finite rather than infinite, if eternal inflation only ran for a finite duration, or if the number of pocket universes is large but bounded, then the copies of you might not exist. There might be a finite number of variations on you, or even just one, but many cosmologists who take eternal inflation seriously conclude that the multiverse is most naturally infinite, and so the copies follow. We do not know which is right. The honest position is that if eternal inflation is correct and unbounded, then the disturbing implication is real. If it is not, then perhaps you are unique after all. The point is not to convince you that there are definitely infinite copies of you. The point is that this is one of the genuinely strange consequences of a serious scientific theory about what came before the Big Bang. Eternal inflation is not a fringe idea. It is a natural extension of the inflation theory that explains the cosmic background. And eternal inflation, taken to its limits, implies a multiverse, and the multiverse, if infinite, implies the copies. The chain of reasoning is straightforward, even if the conclusion is disorienting. This is what physics is doing now, following the equations into territory that would have seemed absurd a generation ago, and reporting back what it finds. So this is one possible picture of before, an eternal multiverse, with no beginning, generating infinite Big Bangs, containing infinite copies of you scattered through endless space. It is one of the most well-developed candidates, but it is far from the only one. Other physicists looking at the same problem have proposed very different stories in which there is no multiverse, but rather a single universe that has lived through many lives, bouncing back and forth between expansions and contractions forever. These cyclic models offer a different kind of before, and they begin with an idea that has reappeared throughout the history of cosmology, that the Big Bang was a beginning but not the first one. If you do not like the multiverse, with its infinite copies of you and its endless cascade of bubble universes, there is another set of proposals to consider. Proposals that try to keep the universe singular while still answering the question of what came before the Big Bang. These are the cyclic models, sometimes called Big Bounce theories, and they share a single radical idea. The Big Bang was not the beginning, but a rebound. The universe in this picture did not begin 13.8 billion years ago. It has always existed, going through endless cycles of expansion and contraction, like a vast cosmic heartbeat that has been beating forever. The basic image is simple, even if the physics is not. Imagine a universe that expands for a very long time, just as ours has, but eventually slows down, stops, and begins to contract. Over more billions of years, the contraction accelerates. Everything draws closer together. Galaxies merge, stars collide, the cosmos compresses toward a smaller and smaller state. Eventually, the contraction becomes so extreme that the entire universe is crushed back into something approaching the conditions of the original Big Bang, and then, instead of vanishing, it bounces. The contraction reverses into a new expansion, a new Big Bang, a new universe similar in structure but with a new history. This idea has a long history in cosmology. In the early 20th century, when the expansion of the universe was first being understood, some scientists wondered whether the expansion might eventually slow and reverse. If it did, the universe might end in a big crunch, the opposite of the Big Bang, a final compression of everything. And if it could end in a big crunch, perhaps it had also begun with a big crunch from a previous universe, which then bounced into ours. The picture was speculative but appealing. It removed the troubling question of a true beginning. The universe was eternal, an endless sequence of bangs and crunches with no first moment to explain. For a long time, the Big Bounce remained mostly a possibility on paper. The difficulty was that in classical general relativity, a contracting universe collapses into a singularity. The same kind of singularity that we have already seen plagues the standard Big Bang picture. A singularity cannot bounce in the classical math. It is a true endpoint, beyond which the equations do not continue. So a classical Big Bounce was, strictly speaking, not possible. The contracting universe would crush itself into nothingness, and there would be no rebound. But here, again, the breakdown of general relativity at high densities becomes the opening. If the singularity is not real, but rather an artifact of an incomplete theory, then there may be no true endpoint after all. In theories of quantum gravity, the would-be singularity is replaced by something more interesting, a state in which space and time become quantized, with a minimum scale below which they cannot be compressed. If space has a minimum scale, then a contracting universe cannot crush itself to a true point. It can only compress so far, and then it must rebound. The Big Bounce becomes mathematically possible, even natural, once you take quantum gravity into account. In recent decades, this has been developed into serious theories, most notably in the framework of loop quantum gravity. We will look at that framework more closely in the next section. For now, the key point is this. A cyclic universe is no longer an idle speculation. It is a real theoretical option, grounded in the same kind of mathematics that physicists use for inflation and other modern cosmology. In a Big Bounce universe, our Big Bang was the rebound from a previous contraction. Before our Big Bang, there was another universe, one that expanded, lived its full cosmic history, and then contracted back, with its end becoming our beginning. And how long has this been going on? In the simplest versions of the theory, it has been going on forever. The universe is eternal with no first cycle. Each cycle begins with the rebound from a previous one and ends with the rebound into a new one. The total number of cycles in some versions is infinite, stretching back into an unbounded past and forward into an unbounded future. The universe in this picture has no beginning at all. It has always been here, breathing in and out, expanding and contracting, with the Big Bang we observe being just the most recent rebirth in an infinite chain. This is a very different answer to what came before the Big Bang than the multiverse offered. Here, there is only one universe. But it has had many lives. Before our Big Bang, there was a previous universe dying in its own contraction. Before that, another and another. The same physical cosmos, going through endless iterations, each one a kind of reincarnation of the last. It is, in some ways, a more elegant idea than the multiverse. No infinite ensemble of separate worlds, just one world living forever. But it has its own strangenesses, its own implications, and its own disturbing consequences, which we will examine as we go deeper into how such a bounce might actually work. The first step is to look at the specific theory that has done the most to make the Big Bounce mathematically respectable: loop quantum gravity. To make the Big Bounce mathematically real, physicists needed a theory that could describe what happens to space and time at the extreme densities of a collapsing universe, the very conditions where general relativity gives up. One of the most developed attempts at such a theory is called loop quantum gravity, and over the past few decades it has become one of the leading candidates for a true theory of quantum spacetime. What it predicts about the supposed beginning of the universe is striking. In loop quantum gravity, the singularity at the heart of the Big Bang simply does not exist. It is replaced by a bounce. Loop quantum gravity grew out of an attempt to apply the principles of quantum mechanics directly to space and time themselves. In ordinary physics, space and time are smooth, continuous, infinitely divisible. You can imagine cutting a region of space into smaller and smaller pieces forever, with no minimum size. Quantum mechanics, however, suggests that many quantities in nature come in discrete amounts, not continuous ones. Energy in many systems is quantized. Angular momentum is quantized. The pioneers of loop quantum gravity asked, what if space and time are quantized too? What if there is a minimum size of space below which it cannot be divided, just as there is a minimum amount of energy that an atom can absorb? The mathematics, when worked out, suggests that space is indeed quantized in this theory. It is made up of tiny, indivisible chunks, sometimes pictured as a network of loops, hence the name. These chunks of space have a finite size, set by a tiny natural unit called the Planck length, far smaller than any atom. Space is not infinitely divisible. It has a smallest scale, beyond which it cannot be compressed further. And this single feature, if it is correct, changes everything about the Big Bang. In ordinary general relativity, a contracting universe can be compressed without limit until it reaches the singularity, a point of infinite density. But in loop quantum gravity, the contracting universe cannot be compressed below the Planck scale. Long before it reaches the singularity, the quantum nature of space kicks in. The chunks of space having a minimum size resist further compression. They begin to push back, and the contraction, instead of running away into infinity, slows, stops, and reverses. The collapsing universe bounces. The supposed beginning of our cosmos becomes the rebound from a previous one. This is sometimes called the Big Bounce in loop quantum cosmology. The math, worked out in detail by physicists including Martin Bojewald and Abhay Ashtekar, shows that under reasonable assumptions, a contracting universe in loop quantum gravity does not end in a singularity. It ends in a bounce, transitioning smoothly to a new expanding phase. The conditions on either side of the bounce are extreme, temperatures and densities almost beyond imagination, but finite. There is no infinity. The universe passes through a moment of greatest density and then expands again. What this means for our question is clear. If loop quantum gravity is right, there was no singular beginning to our universe. Before our Big Bang, there was a contracting phase, a previous universe, perhaps very much like ours, drawing itself together over billions of years, ending in the bounce that gave rise to our cosmos. The Big Bang was a transition, not a beginning. And the previous universe, in turn, presumably arose from another bounce before that, and so on. The chain could stretch back forever. This is a profound and unsettling picture in its own way. It removes the philosophical mystery of a beginning. There was no first moment, no origin event, but replaces it with a different mystery. Why does the universe bounce at all? What keeps the cycle going? And what was the previous universe like? Did it have galaxies and stars, and were they crushed in the contraction? Did it have time, and what was the direction of that time? Did information from the previous universe survive the bounce and influence the conditions of ours? Or was everything erased? These are real scientific questions, and they are being investigated, but they are far from settled. One disturbing implication is worth noting. In some versions of the Big Bounce theory, almost no information from the previous universe survives the rebound. The conditions at this bounce are so extreme, so close to the Planck scale with such intense compression, that whatever structure existed before is essentially wiped out. The new universe begins almost fresh, with very little memory of what came before. So even though there was a previous universe, in a deep sense, it is unreachable. Its history is erased. We cannot recover it. We can only know that it existed, in the abstract sense, but its specifics are lost forever. The bounce is a kind of cosmic amnesia, erasing the past as it gives birth to the present. So loop quantum gravity offers a concrete, mathematically developed picture of what came before the Big Bang, a contracting universe ended in a bounce of which almost nothing remains in our cosmos. The Big Bang is not the beginning of time, but a phase transition between two cosmic eras. And if the theory is right, the same has happened before, perhaps an infinite number of times. Our universe is one cycle in an endless rhythm. But there is more to say about what such a previous universe might have looked like, and what it means for our cosmos to be a kind of cosmic reincarnation of something that has come before. If loop quantum gravity or a similar bounce theory is correct, then there was a previous universe, a cosmos that existed, ran its full course, contracted, and was crushed into the conditions that gave rise to ours. This is a strange thought, and it deserves a moment to absorb. Before the Big Bang in this picture, there was not nothing. There was a universe much like ours, or perhaps very different, with its own galaxies and stars and possibly its own forms of complexity, slowly drawing itself together over unimaginable spans of time, until it ended in the bounce that became our beginning. What was that previous universe like? The honest answer is that we do not know. Most of the information about it, as we have just discussed, may have been erased by the extreme conditions of the bounce. Its specific arrangement of matter, the positions of its galaxies, the patterns of its history, these are unlikely to have survived. But the general kind of universe it may have been is something we can reason about, even if we cannot reconstruct the details. And what we can say, even in general terms, is unsettling in its own way. In many bounce models, the previous universe is essentially symmetric to ours in a particular sense. Ours expanded from the bounce, the previous one contracted into it. Where our universe began hot, dense, and very compact and has been expanding and cooling ever since, the previous one began spread out and cool, slowly drawing together, growing hotter and denser as it contracted, until the moment of greatest compression, the bounce itself. The two universes meet at that bounce. The end of one was the beginning of the other. The crush that destroyed the previous cosmos was the spark that lit ours. This means that in this picture, the previous universe lived through a very long history. It was not a brief or simple thing. It had its own version of cosmic time, perhaps billions of years of contraction, during which whatever structures had formed in its expansion phase were slowly crushed together. If it had had galaxies, those galaxies would have drawn closer over billions of years. If it had had stars, those stars would have eventually merged or been destroyed. The cosmic web would have collapsed back on itself. The entire grand history of a previous universe ended, in this scenario, in the bounce that began ours. There is something genuinely haunting in this image. Picture, if you can, a cosmos very much like our own, with its 2 trillion galaxies and its long history slowly approaching its end. Its stars are growing closer, its galaxies are colliding more often, its temperature is rising. Whatever beings might have lived in that universe, and we cannot rule out that such beings existed, would have seen in their last cosmic moments the sky growing hotter, the galaxies closing in, the night brightening into a final glare. They would not have known that their dying universe would become the seed of another. They simply would have ended, along with their cosmos, as the great compression carried everything toward the bounce. This is one of the most disturbing implications of the cyclic picture. If a previous universe existed, with the kind of conditions that allowed structure to form, then it may have contained life. We cannot say it did. We cannot say it did not. But the universe before ours in this model ran its course much as ours is running its course now. And just as ours will end someday, in heat death or some other final state, the previous one ended in its own way, by crushing itself into the seed of a new cosmos. Whatever it had built, whatever beings might have looked up at its skies and wondered, was destroyed in the transition. We are, in this picture, the descendants of a universe that no longer exists, whose own story has been almost entirely erased. There is an even more uncomfortable thought. If this cycle has been going on forever, then there have been infinite previous universes, Each one ran its course, gave rise to galaxies and stars and possibly life, and then ended in a crush, becoming the seed of the next. An infinite history of universes, each one a complete cosmos in its own right, each one ending in a kind of fiery death, each one giving birth to the next. The total history of existence in this picture is not a single cosmos with 13 billion years of history. It is an unbounded chain of cosmoses, stretching back forever, with most of them entirely lost to memory. This is the cyclic picture taken seriously. We are not at the beginning of anything. We are one cosmic generation in an endless lineage, with countless previous generations behind us and presumably countless more to come. Our universe is not a unique creation. It is the latest in a sequence whose first member, if there even was one, lies infinitely far in the past. The total story is not one of birth and death, but of endless rebirth, and we are simply the current iteration. What gets erased in this picture, and what disturbs many who think about it, is the very idea that anything is original. Everything that has happened, in some sense, has happened before, not the same details, but the same general patterns of cosmic life and death, repeated forever. And the consequences of that erasure, the way it changes the meaning of our own cosmos, are worth examining directly. The cyclic picture of cosmology, in which our universe is one of an endless chain of cosmoses, raises a peculiar question. If the bounce erases most of the information from the previous universe, what does that mean for the things we care about? What survives and what is lost? The answer, as physicists have worked through the math, is that almost everything that made the previous universe what it was is destroyed in the bounce. The new universe begins almost fresh, carrying very little forward from the cosmos that gave rise to it. And this is, in its own quiet way, one of the most disturbing implications of the theory. Think about what a universe is in detail. It is not just empty space, it is full of structure. It contains galaxies arranged in particular patterns, stars with specific compositions and histories, planets and worlds and perhaps living beings, each with their own stories, their own arrangements of matter, their own particular existence. All of this complexity is the result of billions of years of cosmic evolution. It is not random. It is shaped by everything that has happened in that universe's history. The pattern of galaxies in the sky carries the memory of inflation, of the first stars, of the slow build-up of structure under gravity. The composition of a star carries the memory of the supernovae that came before it. Every part of a universe is, in some sense, a record of its past. In the bounce, almost all of this is erased. The compression is so extreme, the densities and temperatures so high, that the delicate patterns of structure are destroyed. The galaxies are torn apart. The stars are crushed into a hot, dense plasma. The atoms themselves are broken down. Everything that the previous universe had built over its billions of years is reduced to a featureless, homogeneous, almost perfectly smooth state at the moment of greatest compression. What survives the bounce in most models is essentially nothing, just the basic general conditions like the total amount of energy and certain fundamental quantities. The specifics are gone. This is, in a strict mathematical sense, a kind of cosmic forgetting. The previous universe had a history, a story, a particular pattern. The new universe inherits almost none of it. The Big Bang that gave rise to our cosmos was, from this perspective, a moment of nearly perfect cosmic amnesia. Whatever the previous universe had built, its galaxies, its stars, its lives, is lost. The information is, in most models, irrecoverably destroyed. Our universe began with almost no memory of what came before. There is something striking in this. If you're looking for a beginning to our universe, the bounce provides one of a sort, not an absolute beginning, but a kind of fresh start. The clock of our universe was, in effect, reset by the bounce. We carry no specific memory of the previous cosmos in the structures we see today. The cosmic microwave background, the galaxies, the elements in our bodies, all of these were created within our universe after the bounce. Nothing in our cosmos directly remembers what was here before. It is as if the previous universe was, in every meaningful sense, destroyed, even if its abstract existence was the necessary cause of ours. This raises a question that philosophers have debated for centuries, now placed in a new context. If the previous universe is, for all practical purposes, gone, its history erased, its structures destroyed, its beings, if there were any, ended, then in what sense did it really exist? It is not enough to say it existed in the past because almost no trace of it remains, and we have no way of recovering its details. It is more like an ancestor we can deduce must have existed, but whose specific life we can never know. The cyclic universe has parents, but the parents have left no records. They are gone, and only the abstract fact of their having lived remains, and the same will presumably happen to us. If our universe is one cycle in an endless chain, then someday, in the unimaginably distant future, after all the galaxies have collided and the stars have died, our cosmos too will draw itself together and end in a bounce. Almost everything that has ever happened here will be erased in that compression. The galaxies we know, the stars, the planets, the lives that have been lived on this small world, all of it will be crushed into a featureless state from which a new universe will be born. That new universe will have almost no memory of us. We will in the deepest sense be forgotten, not just by anyone in particular, but by the very fabric of the cosmos itself. This is one of the disturbing things about the cyclic picture. It robs the universe of permanence. Nothing built within a single cycle survives the transition to the next. Everything is local, transient, bounded by the bounce on either side. The universe is eternal in the largest sense, but each cosmic generation is mortal. Civilizations, if they exist, die with their universes. Histories are erased. Only the abstract pattern, the cycle itself, continues. And this is the deep loneliness of the cyclic picture, that for all its eternity, nothing within it is eternal. The whole thing is a sequence of birth and erasure, going on forever, with everything that happens being eventually undone by the next cosmic compression. There are physicists who have tried to build cyclic models that preserve more information from one cycle to the next, models in which some signature of the previous universe survives in subtle features of the new one. And one of these proposals, perhaps the most ambitious and the most beautiful, comes from one of the great minds of 20th century physics. It is called conformal cyclic cosmology, and it was developed by Roger Penrose. To understand it, we have to set aside almost everything we have just said about the Big Bounce, because Penrose's idea is something stranger. Roger Penrose is one of the great living mathematicians and physicists, a Nobel laureate whose work on general relativity helped establish the modern theory of black holes and the singularity theorems that troubled cosmology for half a century. So when Penrose, late in his career, proposed a radical theory about what came before the Big Bang, the field took notice. The theory is called conformal cyclic cosmology, and it is one of the strangest, most beautiful, and most controversial ideas in modern cosmology. It is also, in its way, profoundly disturbing, but in a different way than the Big Bounce. Where the bounce erases the previous universe in a violent crush, Penrose's theory says something even more unsettling. That the previous universe never really ended, and that we are, in a precise mathematical sense, the continuation of an infinitely old cosmic evolution. To understand Penrose's idea, we need to consider what the far future of our own universe will look like. The current best understanding is that the universe will expand forever, accelerated by dark energy, with matter spreading thinner and thinner over unimaginable spans of time. Eventually every star will burn out. Every galaxy will lose its stars. Black holes will form, then slowly evaporate over vast eons. Eventually, even the protons that make up ordinary matter may decay, leaving behind only photons, gravitons, and a few other essentially massless particles. The universe, in the very far future, becomes a thin, cold, empty soup of radiation, almost nothing, spread across an enormous and growing volume of space. Penrose noticed something strange about this far future state. In a universe consisting only of massless particles, there is no way to define a scale. Mass and matter set scales, distances between particles, ages of objects, sizes of structures. In a universe with only massless radiation, with no matter to provide reference points, the notion of size and time becomes ambiguous. A vast empty universe of photons, mathematically speaking, looks remarkably similar to a tiny hot universe of photons when you strip away the absolute scales. The geometry of the two situations, one inconceivably stretched out, the other inconceivably compact, can be matched up using a mathematical operation called conformal rescaling. This is where Penrose made his leap. What if he asked the far future of our universe, the cold, empty, scaleless state at the end of cosmic history, is, in the appropriate mathematical sense, equivalent to the hot, dense, scaleless state at the beginning of a new universe? What if the end of one cosmic era is, by a conformal rescaling, the beginning of the next? In this picture, the universe does not bounce in the usual sense, it simply continues. The far future of our cosmos, after everything has died and faded, becomes the seed of a new cosmos, not by compression, but by a kind of geometric rebirth. The end and the beginning are, in a strict mathematical sense, the same. Penrose called these cosmic eras eons. Each eon is a complete cosmic history, beginning hot and dense, expanding, forming galaxies and stars and possibly life, eventually fading into a cold, scaleless state of pure radiation. That cold, scaleless state is then the hot, scaleless state of the next eon, which begins its own expansion, forms its own galaxies, runs its own course, and so on forever. Penrose's universe is not a single cycle of expansion and contraction. It is an endless succession of eons, each beginning where the last ended, with the transition being a kind of conformal continuation rather than a violent rebound. What makes this disturbing in its own quiet way is the consequence for our own universe. If Penrose is right, then our universe is one eon in an infinite sequence. Before us, there was a previous eon, a complete cosmos that ran its course, formed its galaxies, possibly had its own life, and then faded into the cold radiation state that became our Big Bang. Before that, another eon, and another. The chain stretches back forever, with no first aeon. Our universe is not the beginning of anything, it is simply the current chapter in a story without an opening page. And here is the part that distinguishes Penrose's theory from the Big Bounce. In the Big Bounce, the previous universe is erased by the violence of the compression. In conformal cyclic cosmology, the transition is much gentler, a smooth mathematical continuation, not a crush. As a result, some information about the previous eon may survive into ours. Subtle patterns from the death of the previous cosmos may have been imprinted on the conditions at the start of ours. Penrose and his collaborators have looked for such patterns in the cosmic microwave background, faint circular features that might be the echoes of supermassive black hole mergers from the previous eon surviving as imprints in the radiation of our universe. These claimed imprints, sometimes called Hawking points after Stephen Hawking, are highly controversial. Some studies have reported finding them. Others have found no evidence. The debate is ongoing and the data are subtle. But the very fact that Penrose's theory makes a testable prediction that there might be observable echoes of a previous universe in our cosmic background sets it apart from many other speculations about what came before the Big Bang. If we ever find clear evidence of such imprints, it would be one of the most remarkable discoveries in the history of science. Literal traces of a universe that existed before our own, visible to our telescopes today. Whether or not those traces exist, the idea behind them is one of the most striking in modern cosmology. Penrose's conformal cyclic cosmology, usually called CCC for short, deserves a closer look because it offers a uniquely strange and beautiful answer to the question of what came before the Big Bang. To grasp it, we need to follow the logic carefully. The result is a picture in which the universe has no beginning and no end, but rather an unending succession of complete cosmic histories, each one mathematically continuous with the next, all part of a single eternal geometry. It is one of the most ambitious cosmological theories ever proposed, and one of the most genuinely strange. The central idea of CCC, as we have just touched on, is that the far future of one cosmic era is mathematically identical, after conformal rescaling to the early beginning of the next. The key word is conformal. A conformal transformation is a mathematical operation that preserves angles but not distances. It can stretch or shrink things, but it leaves the local shape intact. Penrose argued that in a universe consisting only of massless particles, as the far future of our universe will be, after all the matter has decayed, the absolute scale of distance loses meaning, and only the conformal structure remains. A vast empty universe of photons has the same conformal structure as a tiny hot universe of photons. The two are, in a precise sense, conformally equivalent. So Penrose proposed that we take this seriously. The far future of our universe, when it has become a cold, empty, sailless sea of radiation, is conformally equivalent to a hot, dense, scaleless beginning of a new cosmos. If we glue these together, identifying the end of our eon with the beginning of the next, we get a smooth, continuous space-time that extends across the transition. The new aeon then expands, forms galaxies and stars, runs its course, fades into its own cold radiation state, which becomes the beginning of the next aeon, and so on. The result is a single, infinitely long space-time divided into an infinite sequence of eons by transition surfaces that are mathematically smooth. This is a very different picture from the Big Bounce. There is no compression, no singularity, no crush. The transition between aeons is a smooth conformal continuation. Time in this geometry never ends and never began. It stretches infinitely far in both directions, with our cosmic era being just one slice in an unbounded sequence. The universe is, in the largest sense, eternal, not in the sense that any one cosmos lasts forever, but in the sense that the total geometry has no boundaries. Each aeon is finite in its own measure, but the totality is infinite. There is a price to be paid for this elegant picture, and Penrose has been honest about it. For the transition to work, the far future of each aeon must consist only of massless particles, no protons, no electrons, no atoms. This means that by the end of each aeon, all the massive particles must have decayed or fallen into black holes that themselves eventually evaporate. Standard physics does not, in fact, guarantee this. We know that black holes evaporate via Hawking radiation, releasing their mass as radiation over enormous timescales, but there is no established mechanism by which all massive particles in the universe would eventually become massless. Penrose has speculated that there must be some such mechanism, perhaps a slow decay of mass itself over cosmic time, but this remains conjecture, unsupported by current physics. So CCC requires an additional postulate that is not yet part of confirmed science, that mass somehow vanishes in the far future of each aeon. This is one of the main reasons that the theory remains controversial. It is mathematically elegant, observationally provocative, with its claimed Hawking points in the cosmic background, but it relies on a speculative ingredient that has not been independently established. Most cosmologists view it with interest but skepticism. It is not currently the leading candidate for what came before the Big Bang. But it is taken seriously, and it has shaped the broader conversation about whether the universe might be older than we think. What CCC offers, philosophically, is a kind of eternal recurrence at the cosmic scale. Each aeon is a complete cosmic history, with its own galaxies, its own stars, its own evolution. The cosmos is born, develops, ages, and fades, and then begins again, in a new eon, with a new history, but with the same general pattern. The universe is endlessly creative within each eon, and endlessly cyclical across aeons. There is no end to the story, there never was a beginning. The total geometry has always existed and always will, full of aeons stretching back and forward without limit. For some, this is a comforting picture. The universe has no terrifying singular origin, no anxious question of what came before the first moment. There was always something. There always will be. The cosmos is eternal, in a precise mathematical sense. For others, it is disturbing in a different way, the disturbing knowledge that everything we know, all of cosmic history, is just one chapter in an endless book, that countless previous eons have come and gone, leaving almost no trace, and that ours will fade as well in the unimaginable future. We are not the universe, we are one aeon, an aeon's end. The endless succession will go on without us, as it has gone on without all the aeons before us. And one of the most fascinating things about CCC is that it does claim to leave some trace, faint, controversial, but possibly observable, of those vanished aeons in the sky we see today. If Penrose's conformal cyclic cosmology is right, then our universe was not preceded by nothing, nor by a violently crushed prior cosmos. It was preceded by another full eon, a previous cosmic era, with its own galaxies and stars and supermassive black holes that ran its course and faded into a cold radiation state that became our Big Bang. And here is the part that has captured the attention of observational cosmologists. Penrose has argued that some of the events of the previous eon may have left subtle, observable imprints in the cosmic microwave background. If real, these imprints would be the closest thing science has ever come to observing the universe before our own. The basic idea is this. In the previous eon, supermassive black holes, the kind that sit at the centres of galaxies, would have eventually evaporated through Hawking radiation, releasing enormous amounts of energy as massless particles over very long timescales. The largest of these evaporation events would have been the most energetic processes in the dying eon. According to Penrose, the energy released by these supermassive black hole evaporations would survive the conformal transition into the next aeon, appearing in the new cosmos as faint ring-like patterns of slightly elevated temperature in the cosmic microwave background. Penrose and his collaborator Vahe Gurzadian called these features Hawking points, after Stephen Hawking, whose theory of black hole evaporation is the basis for the prediction. So the claim is striking. When we look at the cosmic background, the oldest light we can see, we might be able to find the faded traces of black holes from a previous universe. Specifically, ring-shaped patches of slightly anomalous temperature scattered across the sky would mark the locations where supermassive black holes in the previous eon released their final energy as they evaporated. The signal, if it exists, would be subtle, small variations in an otherwise nearly uniform background, but it should be detectable in principle by the precise measurements of the cosmic microwave background that modern satellites have produced. Have such Hawking points been found? Here the story becomes complicated, and we need to be careful and honest. Penrose, Gurzadian, and several collaborators have published analyses claiming to find statistical evidence for Hawking points in the cosmic background data. They have identified candidate features and argued that their distribution is unlikely to arise by chance, suggesting that something non-random, possibly the imprints of the previous eon, is present in the data. The papers are detailed, the math is real, and the analyses have been published in respectable journals. However, the claims are highly controversial. Other groups have looked at the same data with different analyses and have not found compelling evidence for Hawking points. Some have argued that the statistical significance of the claimed features is overstated, that the analysis methods favour finding patterns whether or not they are really there, and that the same features can be explained by ordinary fluctuations in the cosmic background without invoking a previous aeon. The standard cosmological model with inflation and ordinary physics can reproduce most of what is seen in the cosmic background, without needing any pre-Big Bang eon at all. So the situation is one of genuine scientific dispute. Penrose and his team see evidence for Hawking points. Many other cosmologists do not. The data, as it stands, does not clearly support the claim, but it does not clearly refute it either. More precise measurements of the cosmic background, from future satellite missions and from increasingly detailed analyses, may eventually settle the question. If Hawking points are real, it will be one of the most extraordinary discoveries in the history of science. Visible evidence in our own sky of a universe that existed before the Big Bang. If they are not, then conformal cyclic cosmology loses its main observational support, and the theory becomes harder to defend. For now, we should hold the possibility carefully. Conformal cyclic cosmology is a beautiful and ambitious theory, and Hawking points are a remarkable potential test. The fact that the theory makes any predictions at all in a field where so many ideas remain stubbornly untestable is itself notable. Penrose has done what many others have not. He has taken a strange cosmological idea and given it specific observable consequences. Whether those consequences hold up is a question for the data, not for armchair speculation. The next decade of cosmic microwave background measurements may tell us whether the universe before our universe has left its signature in the sky, or whether we have been looking at patterns that are not really there. What is striking, regardless of how the data turns out, is the very idea that we might be able to see evidence of a universe before our own. For most of human history, the question of what came before the Big Bang was considered permanently beyond reach, a question that could be asked but never answered. Penrose's proposal, even if it turns out to be wrong in the end, has changed that. It has shown that even the deepest question can, in principle, be brought into the realm of empirical investigation, with predictions that can be tested. The deepest mystery has, at least in this one corner of cosmology, become a scientific problem with possible observational signatures. That itself is a remarkable development, regardless of which theory turns out to be right. Conformal cyclic cosmology, whether or not it turns out to be right in detail, points to a way of thinking about the word beginning that is worth dwelling on. In CCC, the universe has no beginning at all, and not in the sense of no beginning we can find, but in a much stronger sense, the sense that the very concept of a beginning does not apply to the universe as a whole. The total cosmos is an endless succession of eons, with no first one and no last. The word beginning only applies within an eon, not to the totality. And this distinction matters more than it might seem. When we ask, what was the beginning of the universe, we usually mean, what was the first event, the first moment, the origin of everything? This is how the question feels natural to a human mind. We are used to stories with beginnings, birthdays, anniversaries, founding moments. We expect the universe to have one too. Even the standard Big Bang picture seems, at first glance, to provide one. The Big Bang as the first moment, the origin event, the cosmic birthday. The universe began 13.8 billion years ago, and that was that. But conformal cyclic cosmology says something different. In CCC, our Big Bang is the beginning of our aeon. That is real and meaningful, but it is not the beginning of everything. It is the transition from the previous eon to ours, a continuation rather than an origin. And the previous eon had its own beginning, from the eon before and so on, with no first beginning anywhere in the sequence. The universe in the largest sense has no first event. It has always had eons, and there have always been transitions between them, going back forever. This is a subtle but important shift. It does not say that the universe is older than 13.8 billion years in our usual sense. Our aeon is indeed about that old, and the matter and structures we see were created within it. But it says that the universe in the larger sense, the total geometry of all eons, is infinitely old, with our aeon being a recent slice. The word old loses some of its bite here, because in an infinite past, every eon is recent compared to the totality. There is no meaningful age of the cosmos as a whole, because the cosmos has no 0 point against which to measure its age. For some, this is liberating. The question what came before the Big Bang stops feeling like an unanswerable mystery and starts feeling like a question with an answer, namely, the previous eon. And the question what came before that eon has its own answer, the aeon before. The sequence is infinite, but at every step there is a previous aeon, never a void or a stop. The mystery of beginning dissolves into a chain of beginnings, each of which is also an ending of something else. There is no first cause to look for, because every cause has its own cause, going back forever. For others, this is unsettling in its own way. The price of removing the absolute beginning is that nothing is truly original. Our universe is not unique, it is one of an infinite sequence. The Big Bang is not the start of all things, it is merely the start of our aeon. The conditions that gave rise to us were prepared by the previous eon, which was prepared by the one before, and so on. There is no point at which the chain begins, no original spark, no creative moment that started everything. There is only the cycle, going on forever. The universe, in this sense, has no story, only a pattern, repeating without end. There is also a peculiar implication for the meaning of cosmic structure. Each eon in CCC develops its own galaxies and stars and possibly its own forms of life. These are local achievements, beautiful, intricate, complex within their own eon, but they are also impermanent. Each eon eventually fades into the cold radiation state that becomes the next eon's beginning, and almost nothing of its specific structure survives. The only thing that survives, in some versions of the theory, is the faint imprint of the largest events, the supermassive black hole evaporations which appear as Hawking points in the next cosmos. Everything else is, in the strong sense, lost. So CCC offers a particular answer to the question of before. There was always something before, going back forever, in the form of previous aeons. Each eon is complete in itself, and each is forgotten, almost entirely, by the next. The universe is eternal in its overall geometry, but each cosmic generation is mortal. And this answer, though it is far from confirmed and it relies on speculative physics, is one of the most carefully developed pictures of what the deep cosmic past might really be like. It is, in its strange way, the answer of a universe that has always been here and always will be, but that has never been the same twice. We have looked at multiverses and bounces and aeons, 3 families of theories that all propose in different ways that the universe is older than the Big Bang. But there is a 4th approach very different from these that takes the original idea of a true beginning seriously and tries to make it scientifically respectable. It was proposed by Stephen Hawking and James Hartle in the early 1980s, and it is called the no-boundary proposal. In some ways it is the most elegant answer to our question, because it refuses the question itself in a particularly clean way. There is no before the Big Bang, the proposal says, because the universe simply has no boundary, no edge, no first moment, no place where before could begin. To understand the no-boundary proposal, we need to imagine the universe not as a sequence of moments in time, but as a 4-dimensional geometric object, a space-time, with time as one of its dimensions. In the standard Big Bang picture, this space-time has a beginning, a singular point at one end from which time flows outward. The space-time in this picture has a boundary in time, a place where it starts. The question what came before is the question of what lies beyond that boundary, and the answer, in the standard picture, is either nothing or the question is malformed. Hawking and Hartle proposed a different geometry. What if at the supposed beginning the space-time does not have a sharp boundary at all? What if instead the time dimension smoothly curves around and closes up, like the curved surface at the bottom of a sphere? Picture a globe of the Earth. There is no edge to the surface of a globe. You can wander anywhere on it without ever falling off. But there are special points, the poles, where the lines of longitude all meet. The South Pole is a particular point on the globe, but it is not an edge. The surface continues smoothly through it. The no-boundary proposal suggests that the universe is something like this. The Big Bang is not an edge of space-time. It is more like a pole, a smooth, rounded place where time and space are continuous, but where time ceases to be exactly time and becomes something more like another spatial dimension. Just as there is no south of the South Pole, there is no before the Big Bang in this picture, not because the question is forbidden, but because the geometry simply does not extend in that direction. The universe is finite in the past, but it has no boundary. It is closed off at the beginning smoothly without an edge. This is a profound and elegant idea, and it is mathematically precise. Hawking and Hartle proposed a specific formula, the no-boundary wave function, that describes a universe arising in this way, from a state in which there is no boundary and no edge. The universe simply is, in this picture, with the Big Bang as the smooth, rounded tip of its geometry, beyond which the very concept of before has no meaning. It is the formal mathematical realization of Augustine's intuition, 16 centuries later. Time begins with the universe, and there is no before because there is no time in which before could occur. What is striking about the no-boundary proposal is that it makes the question of before not just unanswerable, but specifically meaningless in a way that physics can describe. The geometry is closed at the beginning. The time dimension smoothly transitions into another spatial dimension, and the universe simply emerges without an edge, without a prior moment. The math says this is what it would mean for the universe to have no beginning in the ordinary sense, while still being finite in age. The cosmos is, in a precise mathematical sense, complete in itself, with no need for a before because the geometry does not call for one. Now, the no-boundary proposal is not universally accepted. Different physicists interpret it differently, and there are technical questions about whether it really produces a universe like ours, with the right properties for galaxies and life to arise. In recent years, some cosmologists, including Neil Turok, have argued that the no-boundary proposal, when worked out carefully, predicts a universe quite different from ours, one in which inflation does not happen, and in which large-scale structure does not form. If these criticisms are right, the no-boundary proposal in its original form may not describe our universe. But the basic idea that the universe could be geometrically closed at the beginning without an edge remains one of the most important contributions to our thinking about the question. So the no-boundary proposal offers a different kind of answer to our question. Instead of pushing the beginning back further into a multiverse or a bounce or an aeon, it accepts that our universe has a finite age, but argues that this finite beginning is not an edge, not a wall, but a smooth closure of space-time itself. There is no before because there is nothing in the geometry that corresponds to before. The question dissolves into the structure of the universe itself. This is, in its own way, both the most conservative and the most radical answer we have considered. It keeps the Big Bang as a real beginning, but redefines what beginning means. Stephen Hawking, who co-developed the no-boundary proposal, was famous for a particular way of explaining why the question what came before the Big Bang might be malformed. He compared it to asking what lies north of the North Pole. The comparison is so clean, so vivid, that it has become one of the standard ways of communicating this difficult idea to non-physicists. And it is worth dwelling on, because it captures something essential about how time may work at the boundaries of the universe. Imagine the surface of the Earth. It is a two-dimensional surface curved into a sphere, and it has a particular property. At every point you can move in 4 cardinal directions, north, south, east, and west. The surface has no edges. You can keep walking forever in any direction without falling off. But there are special places where the directions get strange. At the North Pole, every direction is south. There is no north of here, because you have reached the northernmost point. The question what is north of the North Pole is not difficult to answer because the answer is mysterious. It is impossible to answer because the question is malformed. North runs out at the pole. There is no direction further north to point to. Hawking proposed that before works the same way at the Big Bang. Time has a direction, past and future, just as the surface of the Earth has directions. At ordinary moments, you can go in either direction, into the past or into the future. But at the Big Bang, just as at the North Pole, the direction toward the past simply runs out. There is no time further back. The question what was before the Big Bang is not difficult because the answer is mysterious. It is impossible because the question presupposes a direction that does not exist. Past runs out at the beginning just as north runs out at the pole. The question is malformed in exactly the same way. This analogy is powerful because it gives us a concrete way of imagining a situation that is otherwise almost impossible to picture. Most people, when they try to imagine the Big Bang as a beginning, picture a wall, a kind of barrier behind which something might lie. But a pole is not a wall. The surface of the Earth continues smoothly through the North Pole. There is no barrier there. It is simply that the direction in question runs out. You can stand at the pole and look in any direction, and every direction is south. There is nothing missing. There is just no further north. In the same way Hawking suggested, the universe at the Big Bang is not bounded by a wall, but by a smooth closure of time. Time runs out at that moment, not because something is blocking it, but because the geometry of the universe simply does not extend in that direction. The Big Bang is not a place where something stops, it is a place where the question of before stops having meaning. And once you understand this, you stop trying to imagine what was on the other side of the wall, because there is no other side, just as there is no north of the North Pole. For many people, this is a genuinely satisfying answer. It dissolves the apparent paradox of the beginning. The universe is finite in age, but it does not need a before because the very concept does not apply. The question that seems so urgent, what was there at the start, becomes a question we no longer need to answer, because it was a confused question all along. The cosmos is what it is, beginning at the Big Bang, complete and self-contained, with no need for a prior cause or condition. But there is, of course, a difficulty. The analogy works only if time really does behave like the surface of the Earth at the pole, only if time runs out smoothly at the Big Bang, with no edge and no boundary. And this is exactly what the no-boundary proposal asserts, but it has not been proven. Other theories, as we have seen, suggest that time does not run out at the Big Bang at all, that it continues in some form into a previous eon or a contracting phase or an inflationary substrate. In those theories, the Big Bang is not the North Pole. It's more like the boundary between two countries with another country lying on the other side. The question what is on the other side is then not malformed at all. It has an answer, even if we cannot easily reach it. So Hawking's analogy is illuminating but not conclusive. It tells us what it would look like geometrically for there to be no before the Big Bang, but it does not tell us whether the universe is actually that way. The honest position is that we do not yet know. Time may run out at the Big Bang, as Hawking suggested, or it may continue in some form into a region we have not yet been able to describe. The two possibilities are still open, and which one is correct depends on physics we have not yet pinned down. The most we can say is that before the Big Bang may be either a meaningful question with an answer, or a malformed question with no answer, and we do not yet know which. This is, in a way, the most disturbing thing about the whole investigation. The question we have been asking, what came before the Big Bang, may not have a single right answer, or even a single meaningful form. Different theories give different kinds of answers. Some preserve a meaningful before, some dissolve it. Without knowing which theory is correct, we cannot even be sure whether our question is the right question to ask, and yet we have to ask something. The mystery of beginning is too deep to simply set aside, and so we move on to other proposals, knowing that we may be asking malformed questions, and trying to think carefully, even so. So far we have looked at multiverses, bounces, eons, and the no-boundary proposal. There is another idea, more recent and stranger in its way, proposed in the last several years by physicists including Latham Boyle, Neil Trock and Kieran Finn. They call it the CPT symmetric universe, and it offers a strikingly different answer to our question. Not that the universe began with the Big Bang, and not that it came from a previous universe in a forward time direction, but that for every moment of our universe, there is a mirror moment in another universe, running backwards. The Big Bang in this picture is not the beginning of our universe alone. It is the meeting point of our universe and its mirror twin, which extends in the opposite direction of time. The idea grew out of an observation about a deep symmetry in physics called CPT symmetry. CPT stands for charge, parity, and time. According to one of the most fundamental theorems in physics, the laws of nature are unchanged if you simultaneously reverse all electric charges, mirror reflect space, and reverse the direction of time. Together, these three operations leave the physics invariant. It is one of the most robust symmetries we know of, deeply embedded in the structure of quantum field theory. Boyle, Turok, and Finn took this symmetry seriously and applied it to cosmology. Suppose, they said, that the universe as a whole respects CPT symmetry, not just the local laws of physics within it, but the cosmos itself at the largest scale. Then for every solution describing our expanding universe, there should be a CPT mirrored solution. The mirrored solution would have all charges reversed, all spatial directions mirrored, and time running backwards. The total universe in this picture consists of both halves, ours and its mirror image, meeting at the Big Bang. What does this mean concretely? Imagine our universe expanding from the Big Bang into the future, as it has been doing for 13.8 billion years. Now imagine on the other side of the Big Bang a mirror universe expanding into what we would call the past, but in its own frame it is expanding into its future, with time running in what is for us the reverse direction. The two universes share the Big Bang as their common starting point, but they extend in opposite time directions. From our perspective, the mirror universe is in our past. From its perspective, we are in its past. Together, they form a single CPT symmetric whole. This is a strange and disturbing picture in its own way. It does not give the universe a true before in the ordinary sense. The mirror universe is not in our past in any way we could ever access, but it does give the Big Bang a different meaning. The Big Bang is not the absolute beginning of all reality. It is the meeting place of two cosmoses, each one a mirror of the other. The total universe in this view is doubly large, twice the cosmos we observe, with the matching half hidden in the opposite time direction. The theory has some remarkable consequences. For one thing, it does not require inflation. The CPT symmetric universe naturally produces the kind of uniformity that inflation was invented to explain, because the symmetry imposes constraints on the conditions at the Big Bang. For another, it predicts specific properties of the cosmos that can, in principle, be tested. The theory predicts, for example, that the universe should contain a specific kind of neutrino, a right-handed neutrino with particular properties, which could be detected by future experiments. If detected, it would be strong evidence for the theory. If ruled out, the theory would have a serious problem. The theory is also notable for its philosophical economy. It does not require a multiverse of countless bubble universes. It does not require an infinite chain of bounces or eons. It says simply the universe is twice what we see mirrored across the Big Bang, with the two halves connected by a deep symmetry of physics. The Big Bang is not eliminated as the universe's beginning. It is just reconceived as a meeting point, with the universe on the other side being a kind of mirror reflection rather than a prior epoch. In some interpretations of this proposal, the mirror universe contains its own galaxies, its own stars, its own possible lives, beings who experience time as flowing forward, even though from our perspective they live in our distant past. They cannot communicate with us, the mirror is sealed by the symmetry. But they may be there, in a precise sense, mirroring our cosmos across the boundary of the Big Bang. Whether or not there is anything there to be conscious in the mirror is unanswered, but the symmetry implies that the structure exists, even if we cannot interact with it. This is one of the newer proposals, less developed than inflation or loop quantum gravity, but it has gained attention because it is mathematically elegant and makes specific predictions. It is also one of the more unsettling in a particular way, not because it implies infinite copies of us or endless cycles, but because it implies that the universe is doubled, hidden behind a symmetry with a mirror half that we will never see and never reach. The Big Bang in this view is not a wall or a pole, but a mirror, and beyond the mirror is another universe running in the opposite direction, fundamentally inaccessible to us. String theory, the most ambitious attempt at a unified theory of all of physics, offers its own peculiar answer to the question of what came before the Big Bang. In string theory, the fundamental constituents of nature are not point particles, but tiny vibrating strings, and the universe is not necessarily a single four-dimensional spacetime. Instead, our universe may be one of many branes, higher dimensional surfaces, floating in a larger space of extra dimensions. And the Big Bang, according to one version of this story, may have been caused by a collision between two such brains. To grasp this idea, we need to set aside our ordinary picture of the universe as 3 dimensions of space plus 1 of time, and accept the possibility that there are more dimensions than the ones we see. String theory typically requires either 10 or 11 total dimensions of spacetime to be mathematically consistent. The extra dimensions are not visible to us because they are either rolled up very small or because we are confined to a lower dimensional subspace within the higher dimensional whole. This subspace is called a brane, short for membrane, and our entire observable universe, every galaxy, every star, every particle, may be confined to a single such brane, floating in the larger higher dimensional space. If our universe is a brane, then it makes sense to ask whether other branes exist nearby. In some string-theoretic models, the answer is yes. There may be many branes, each one a possible universe, separated from ours by small distances in the extra dimensions. We cannot see these other branes because light and matter on our brane cannot leave it, but gravity in some versions of string theory can. The branes can interact gravitationally, and under certain conditions they can even approach each other. This sets the stage for the ekpyrotic scenario, proposed in the early 2000s by Paul Steinhardt, Neil Turok and others. In the ekpyrotic picture, our universe was caused by a collision between 2 branes. Before the Big Bang, there were 2 branes separated by a small distance in the extra dimensions, slowly drifting toward each other under the influence of forces between them. The branes were cold, empty and quiet, having existed for a very long time. Then, slowly and inevitably, they began to approach. As they neared each other, the empty space between them grew increasingly tense like a stretched rubber band, and eventually they collided. The collision in this picture was the Big Bang. The energy of the impact, spread across our brane, became the hot, dense state that we have always called the early universe. The matter and radiation that fill our cosmos today are the energy of the collision, slowly cooling and condensing into the structures we see. The Big Bang was not a singular event from nothing. It was a violent encounter between 2 pre-existing surfaces in a higher dimensional space, and the universe we live in is the imprint of that encounter on one of those surfaces. What came before the Big Bang in this picture is clear. Before the Big Bang, there were 2 branes drifting toward each other. Before that, the branes existed for a very long time in a kind of cosmic isolation, far enough apart that nothing was happening. And presumably before that, the same or some similar configuration extended back further. In some versions of the theory, the branes have always existed, going through endless cycles of approach, collision, and rebound. Each collision produces a new Big Bang on the brane, a new universe, and then the brane settles back into a long, cool, quiet phase until the next approach begins. This is one form of the cyclic universe, different from the loop quantum gravity bounce, in that the cycle takes place between branes in higher dimensions rather than between expansion and contraction of a single space. But the spirit is the same. The universe has no first event, only an endless sequence of brane collisions, with our Big Bang being just the most recent in an infinite series. Before our universe, there was another brane collision, producing another universe much like ours. Before that, another. The chain stretches back forever. The ekpyrotic scenario has some advantages over simpler bounce models. It does not require the universe to compress itself into a singularity to bounce. The collision is between 2 distinct finite branes, which never reach infinite density. It can naturally explain some features of the cosmic background that inflation was invented to handle. And it is grounded in string theory, one of the most developed mathematical frameworks for unifying physics. But it has disadvantages too. It relies on speculative aspects of string theory, extra dimensions, branes, certain kinds of forces between them that have not been independently confirmed. There is no direct experimental evidence for branes or for the extra dimensions they would live in. And string theory itself is not yet complete. We do not have a single agreed upon version, but rather a landscape of possible string theories, each with different predictions. So while the ekpyrotic scenario is mathematically beautiful and conceptually striking, it depends on a larger framework that is itself unconfirmed. It is one of the more exotic proposals for what came before the Big Bang, and it deserves a closer look at the actual mechanism, the collision of branes in a higher dimensional cosmos. The word ekpyrotic comes from a Greek term meaning out of fire, and it was chosen by Steinhardt and Turok to evoke the ancient Stoic idea that the universe periodically dissolves into a great cosmic fire and is reborn from it. The modern ekpyrotic theory is, of course, not based on Stoic philosophy, but on string theory and higher dimensional geometry, yet the image is fitting. In the ekpyrotic picture, our universe was born from a great cosmic fire, the fire generated by the collision of two brains in a higher dimensional space, and that fire was, in turn, the death of the previous brain configuration. Each universe is born from the fire of the previous, in an endless sequence. To understand the ekpyrotic universe more concretely, let us follow the cosmic story it tells. Begin with two brains, our brain and another, separated by a small gap in the extra dimensions. The brains are cool, empty, and nearly featureless. They have been in this state for an enormously long time, perhaps trillions of years. There is almost no matter on either brain. Everything has decayed or been diluted away by the long quiet phase. The brains are essentially blank canvases, waiting for the next event. Slowly, over those trillions of years, forces in the extra dimensions begin to draw the brains together. The motion is gentle and inexorable. As the brains approach, the energy stored in the field between them, the field that mediates the attractive force, begins to grow. Eventually, the brains come close enough that they collide, smashing together across their entire extent simultaneously. The energy of the collision is enormous, far greater than anything in ordinary cosmic history, and it is released directly into the matter of the brains. This release of energy is what creates the hot, dense state we call the Big Bang. From the perspective of any observer on a brain, the moment of collision is the beginning of their universe. Suddenly, the brain that had been cold and empty for trillions of years is filled with intense heat and matter. This is the early universe, the hot, dense plasma that we have always associated with the Big Bang. From here, the standard story unfolds. The universe cools, particles and atoms form, galaxies and stars and life eventually appear, and the universe expands and ages until eventually it becomes cool and empty again, ready for the next cycle. What is striking about this picture is that the Big Bang is not a singular event from nothing. It is a finite, energetic collision with a clear cause, the meeting of two pre-existing brains. There is no infinity, no singularity, no place where physics breaks down in the same dramatic way it does in the standard picture. The math, in the ekpyrotic scenario, remains finite throughout. The Big Bang is intense but not infinite. It is the impact of two brains and the energy released is bounded. The cycle continues. After the collision, the brains separate again. The newly hot cosmos on each brain begins to cool. Over many billions of years, galaxies and stars form. Eventually, in the far future, the matter on each brain spreads out, the stars die, and the brains become cold and empty once more. The cycle is set for the next iteration. The brains will drift together again, collide again, and another universe will be born from the fire of the meeting, and so on, forever. This is one of the more developed alternatives to inflation, and Steinhardt and Turok have championed it for over 2 decades. They have argued that it solves several of the same puzzles that inflation was invented to handle, without requiring the somewhat awkward features of inflation, like the eternal inflation that produces multiverses and infinite copies of us. The ekpyrotic universe is more economical in their view, a single cycling cosmos, repeating its history forever without the metaphysical extravagance of countless bubble universes. But like all the proposals we have looked at, the ekpyrotic picture has its difficulties. It depends on speculative aspects of string theory. It requires specific kinds of brains and forces that we have not directly observed. Its predictions for the cosmic background, while compatible with current data, differ in some subtle ways from those of inflation, and it is not yet clear which set of predictions the data favours. Some recent results have been argued to support inflation over ekpyrotic models, while others remain ambiguous. The contest is not yet settled. What the ekpyrotic universe shows, regardless of whether it is ultimately right, is the range of serious scientific proposals for what came before the Big Bang. It is not pure speculation. It is grounded in mathematical frameworks that physicists have spent decades developing. And it offers a particular kind of answer, a previous brain configuration, drawing together over trillions of years, ending in the fire that became our Big Bang. The cosmos is eternal in this picture, but each universe is mortal. Each one ends in cold emptiness, becomes the canvas for the next, and the cycle goes on, fueled by the slow drift of brains through dimensions we cannot see. It is a remarkable story, and it is not the strangest one we will consider. Because there is one more proposal, perhaps the most radical of all, which says that the universe came from literally nothing, and that this nothing was the source of everything. We have looked at theories in which the universe came from a multiverse, from a bouncing previous cosmos, from a previous eon, from a brain collision, and from a closed geometry with no boundary. There is one more major proposal worth considering, and it is perhaps the most radical of all. It was developed by Alexander Vilenkin and others in the early 1980s, and it proposes that the universe came, quite literally, from a nothing, that there was no before because there was no anything, and that the universe arose by a process called quantum tunneling out of a state of absolute non-existence. To grasp this, we need to remember a peculiar feature of quantum mechanics. In classical physics, a particle that does not have enough energy to climb a barrier simply cannot get to the other side. In quantum mechanics, however, the particle has a small but real probability of appearing on the other side without climbing, a process called tunneling. Tunneling is real. It has been observed in countless experiments, and it is essential to phenomena like nuclear fusion in the sun and the operation of certain semiconductor devices. In quantum mechanics, things can pass through barriers they classically cannot cross, simply by virtue of quantum uncertainty. Now imagine applying this idea to the universe itself. Suppose that at the deepest level the universe is governed by quantum mechanics, and that the very existence of a universe can be thought of as a kind of quantum state. Then, in principle, a universe could tunnel into existence from a state of non-existence, not from empty space, which is itself something, but from a state in which there is no space, no time, no anything. The universe, in this picture, would emerge as a quantum fluctuation out of literal nothingness, by the same kind of process that allows particles to tunnel through barriers in ordinary quantum mechanics. This is the quantum tunneling proposal, sometimes called Vilenkin's tunneling universe. It says, in essence, that the universe can come from nothing, not as a poetic phrase, but as a precise physical claim about quantum mechanics applied to cosmology. The nothing here is not empty space. It is the absence of any space-time, any geometry, any physical structure. From this absolute nothing, a tiny universe emerges by quantum tunneling, and once it exists, it can grow and develop into the cosmos we see today. There was no before because there was no time. The universe simply appears by quantum chance out of non-existence. This is, in its way, the most disturbing answer to our question yet. It is not that the universe came from something else, like a previous universe or a multiverse. It is that the universe came from nothing. There was no prior state, no source, no cause. The cosmos is a quantum fluctuation, and asking what came before is like asking what causes a particle to tunnel through a barrier at a particular moment. There is no cause in the ordinary sense. There is only a probability, and the universe happened to be the realization of that probability. Some philosophers and theologians have objected to this picture, arguing that nothing in the physicist's sense is not really nothing, that it still presupposes the laws of quantum mechanics, the structure of probability, the framework in which tunneling can happen. Nothing, they argue, would have no quantum mechanics, no probability, no anything at all. So the universe did not really come from absolute nothing, it came from a kind of quantum vacuum which is not nothing. This is a fair point, and Vilenkin and others have acknowledged it. The nothing in the tunneling proposal is the absence of space-time, not the absence of physical law. The laws are still there, providing the framework in which tunneling can occur. So in the strictest philosophical sense, the universe does not come from absolute nothing. It comes from a state in which there is no space, no time, no matter, no energy, but in which the laws of physics still apply, including the laws of quantum mechanics that make tunneling possible. Even so, this is a remarkably austere starting point. The universe does not need a prior universe to come from. It does not need a multiverse to be one bubble in. It does not need a previous eon to continue from. All it needs is the bare framework of physical law, and then a quantum fluctuation can produce a cosmos out of nothing. The nothing is as close to absolute non-existence as physics allows itself to imagine, and the universe is the result of a chance event in that nothing. What does this mean for our question? It means that, in this proposal, the answer to what came before the Big Bang is genuinely nothing. Not the question is malformed, and not a previous universe, but nothing in the sense of absolutely no physical state. The universe is a quantum tunneling event from non-existence, and the very concept of before does not apply because there was no time and no anything. The cosmos is, in this picture, a kind of ontological miracle. an unprompted appearance with no prior cause, made possible only by the strange logic of quantum mechanics. And to understand what this nothing really means, in the careful physicist sense, we have to look closely at the surprising structure of nothing itself. The word nothing is one of the most slippery in the English language. In ordinary speech, we use it to mean an absence, a lack, the opposite of something. But when physicists talk about the universe coming from nothing, they mean something more specific and more strange. The nothing of physics is not the simple absence of stuff. It is a precise mathematically defined state, one that, when you look closely, is not really empty at all. To understand the quantum tunneling proposal and several of the other theories we have considered, we have to spend some time with this strange nothing and what it really means. In ordinary intuition, nothing is the absence of everything. No matter, no energy, no space, no time, just absolute non-existence. The trouble is that this kind of nothing is hard to describe scientifically, because science is in the business of describing states, and a true absence of everything is not really a state at all. There are no equations for it, no properties to assign, no way to do calculations with it. If you push the concept of nothing all the way to its philosophical extreme, you arrive at something so featureless that it cannot be the subject of physics at all. So physicists have, perforce, used the word nothing in narrower senses. The most common is the quantum vacuum and the lowest energy state of empty space. This is what physicists usually mean when they talk about empty space. It is not absolutely empty. Quantum mechanics tells us that even in the most carefully evacuated region of space, with all matter and radiation removed, there is still a residual activity, virtual particles popping in and out of existence on tiny timescales, fluctuating fields that cannot be entirely silenced. The quantum vacuum is the closest thing physics can get to empty space, and even it is bubbling with activity. It is, in a sense, a kind of nothing, but not absolute nothing. It is the nothing of physics. When we say the universe could come from a quantum tunneling event, we usually mean it came from something at least as elaborate as a quantum vacuum, or perhaps even less, but still with quantum mechanical structure. Vilenkin's nothing, for example, includes the laws of quantum mechanics and a particular kind of wave function that describes the probability of universes coming into existence. It does not include space, time, matter, or energy, but it does include the mathematical framework within which these things can emerge. This is not nothing in the philosopher's sense. It is a stripped-down nothing, a no-space, no-time state, but with the rules of physics still intact. For some, this is a serious objection to the claim that the universe came from nothing. If the nothing includes physical law, then it is not really nothing. It is a particular kind of something. The deepest question, why is there anything rather than absolutely nothing, is not really answered. It is just pushed back. Why are there laws of physics? Why does quantum mechanics exist? These questions remain even after the universe is explained as a quantum tunneling event from physical law nothing. For others, this is the best we can do, and it is much better than the previous best. Before quantum cosmology, the question of where the universe came from had no scientific answer at all. The tunneling proposal at least gives a framework in which the question has a partial answer. The universe came from no space-time by a quantum process, given the laws of physics. The fact that this does not fully explain the laws themselves is a remaining mystery, but it is a smaller mystery than the one we started with. The vast bulk of cosmic existence has been derived from the bare framework of physical law and a quantum fluctuation. What is striking is how strange the physicist's nothing turns out to be. It is not the simple void of common imagination. It is a state defined by what is absent, space, time, matter, but rich in what remains, the laws, the structure, the framework. It is more like a possibility space than a void, a set of rules waiting to produce something rather than an absolute blank. And from this possibility space, the universe can emerge by chance, by a quantum event with a definite probability. This is, in its way, both more and less mysterious than the simple picture of a void giving rise to a cosmos. More mysterious, because the structure of physical law is itself unexplained. We do not know why the laws are what they are, why quantum mechanics is true, why the universe has the particular framework it does. Less mysterious, because at least the appearance of a universe from this nothing is a definite process, governed by definite probability, with definite consequences. The cosmos is no longer a creation from absolute nothingness. It is a quantum fluctuation in a state of structured non-existence. So when you hear that the universe came from nothing, hold on to the physicist's meaning. The nothing is not absolute non-existence. It is a state without space and time, but with the rules of physics still present. The cosmos emerged from this state by a quantum process, and, before, did not exist because time itself was part of what emerged. It is the best honest answer physics has to offer, and like all the proposals we have considered, it leaves some questions unanswered while resolving others. The whole investigation reaches a peculiar kind of summit here, and from this summit, we can finally take stock of what these theories share and what they all imply about our place in things. We have now surveyed 7 major scientific proposals for what came before the Big Bang: inflation and its eternal extension, the big bounce of loop quantum gravity, Penrose's conformal cyclic cosmology with its endless eons, the Hartley-Hawking no-boundary proposal, the CPT symmetric mirror universe, the ekpyrotic brain collision, the quantum tunneling from nothing. Each of these is a serious scientific idea, developed by serious physicists grounded in real mathematics. And here is the disturbing truth that emerges when you look at all of them together. They cannot all be right, but each of them is, in its own way, deep. There is no comfortable answer hiding in the set. Every candidate, in some respect, disturbs the ordinary picture of what the universe is. Consider what each one implies. Eternal inflation suggests that our universe is one of infinitely many bubble cosmoses in an endless inflating substrate, with no first event and infinite copies of you scattered through the multiverse. The Big Bounce suggests that our cosmos is the latest in an endless sequence of compressions and rebounds, with the previous universe crushed almost entirely into ours. Conformal cyclic cosmology says we are one eon in an infinite chain, with each cosmos fading into the next, leaving only faint scars in the cosmic background. The no-boundary proposal says the universe simply has no before, because the geometry forbids it. Time runs out smoothly at the beginning. The CPT symmetric universe says our cosmos has a mirror twin, running backwards in time on the other side of the Big Bang. The ekpyrotic universe says we were born from the collision of higher dimensional brains, with the cycle going on forever. Quantum tunneling says the universe came from nothing, from a state without space or time, by a quantum fluctuation with no prior cause. Each of these is strange, each leaves something deeply unsettling in its wake. There is no proposal in which the universe began at a single ordinary moment, with a clear cause, in a way that matches everyday intuition. The very best science has to offer, when applied to the question of cosmic origins, is a set of options each more disorienting than the last. We do not get to escape the disturbance by picking the right theory. Every theory disturbs, and here is the further disturbing truth. We do not know which of these is correct. We may never know. The conditions of the very early universe, the region just before the Big Bang, or the structure beyond the singularity, are not directly observable. We see only the cosmic microwave background, the wall of oldest light, and through it we can infer some things but not everything. The differences between the theories often manifest in subtle signatures, small features in the cosmic background, particular patterns of gravitational waves, specific predictions about exotic particles that may or may not be detectable with present or future technology. Some of the theories make predictions we can in principle test, others do not, and for the foreseeable future, several of these proposals will remain viable, with no clear way to decide between them. So the situation is this. The deepest question of all, what came before the Big Bang, has been moved from the realm of pure speculation into the realm of serious scientific investigation. We have multiple developed proposals, each with its own mathematics and its own consequences. We have made enormous progress in being able to ask the question precisely, but we have not solved it. We do not know which proposal, if any, is correct. We may never know. The investigation continues, but it may continue indefinitely, with the question of cosmic origins remaining open for as long as humanity exists. This is a kind of disturbing in itself. It is not the disturbance of finding a specific unsettling answer. It is the disturbance of facing genuine, possibly permanent uncertainty about the deepest question we can ask. We may live our entire lives, and our species may live its entire history, without ever being able to choose between these candidate origins. The truth about what came before the Big Bang may simply lie beyond the reach of observation, locked behind the cosmic microwave background, in a region of space and time we can never directly examine. And yet the very fact that we can ask the question scientifically, that we can develop precise mathematical proposals and explore their consequences, is itself a remarkable achievement. The question that for thousands of years was the province of philosophy and religion is now also a question for physics. We may not solve it, but we are approaching it with the tools of science, and we are making real progress. The candidates have narrowed, the questions have sharpened, the implications have become clearer. Even if we never reach a final answer, the journey of asking is one of the most extraordinary things our species has ever done. There is a kind of nobility in this. The careful, patient work of trying to look behind the wall, knowing we may never see clearly, knowing that whatever we find may be too strange to fully grasp. We are small beings on a small world, asking the largest question there is. We have built the mathematics, run the simulations, scanned the cosmic background, proposed the theories. We have done what minds like ours can do, and we have come back with 7 proposals, each disturbing in its own way, none of them yet proven, all of them taking us further from any simple story of beginning. That is where modern science stands, and the question of why we cannot simply pick the right answer, why the question may remain open for a very long time, or forever, deserves a moment of its own. We have looked at 7 major proposals for what came before the Big Bang, and we have noted that we do not yet know which is correct. Now it is worth dwelling on why we may never know, because the obstacles to choosing among these theories are not just practical, not just a matter of needing better telescopes or more clever experiments. The difficulties are deeper than that. Some of them may be permanent, built into the very structure of the question we are asking. The universe may have arranged things, in effect, so that the answer to our deepest question is forever just beyond our reach. The first obstacle is the cosmic microwave background itself. We have already discussed how this wall of oldest light blocks our view of anything earlier. We can see with our telescopes the universe as it was 380,000 years after the Big Bang. We cannot see the first 380,000 years directly, because the universe was opaque before then, and we certainly cannot see anything from before the Big Bang itself. The information about the very early universe, and certainly about any prior state, is hidden behind this fog of light. We can only infer indirectly by looking at how the early universe shaped the patterns of structure we observe today. This indirect inference is powerful, but it is limited. The cosmic microwave background, and the distribution of galaxies and the abundances of light elements all carry imprints of conditions in the early universe. But the imprints are subtle, and many different early conditions can produce the same broad features. To distinguish, say, between inflation and ekpyrotic models, we need to look at fine details, the precise statistical patterns of the background fluctuations, the polarization of the microwave light, the spectrum of gravitational waves from the very early cosmos. These signals are small, hard to measure precisely, and easily contaminated by other effects. Distinguishing them may take decades or longer, and even then, the differences may turn out to be too subtle to settle the question definitively. There is a deeper obstacle. Some of the theories we have considered make predictions that are, in principle, untestable. If our universe is one bubble in an eternally inflating multiverse, the other bubbles are forever beyond our horizon, separated by inflating space we can never cross. We cannot detect them directly. We can only ask whether the existence of a multiverse is consistent with what we see in our own universe, which is a much weaker form of test. The multiverse is unobservable in principle, not just in practice. The same may be true of the mirror universe in the CPT symmetric model, or of the previous eon in conformal cyclic cosmology. The structures these theories postulate may exist, but lie permanently outside our possible experience. A third obstacle is the lack of a complete theory of quantum gravity. To describe the conditions at or before the Big Bang, we need to combine general relativity with quantum mechanics in a way that no one has yet fully achieved. Loop quantum gravity, string theory, and other candidates each offer pieces of the puzzle, but none of them is a complete tested theory. Without quantum gravity, our predictions about the deepest moments of cosmic history have unavoidable uncertainties, and different versions of quantum gravity give different answers. Until we have a working theory of quantum gravity, which may take decades or centuries to develop, many of these proposals remain mathematically incomplete, and we cannot make sharp comparisons between them. There is also a more philosophical difficulty. The question what came before the Big Bang may, in some theories, simply have no answer. In the no-boundary proposal, as we have seen, there is no before, because the geometry does not extend in that direction. In the quantum tunneling proposal, there is no prior physical state. The universe simply emerges from a quantum fluctuation in a state without space or time. These are not failures of investigation. They are claims that the question itself is malformed. If one of these theories is correct, then there is no fact of the matter about before the Big Bang. There is just the universe we have, with no prior state to discover. Asking what was there is like asking what is the colour of jealousy. The question has no answer because it presupposes something that does not exist. So the difficulties pile up. The observational evidence is indirect, subtle, and limited by the cosmic background wall. Some of the theories make predictions we cannot test in principle. The quantum gravity needed to make sharp predictions is not yet available, and the question itself may be malformed in some of the candidate theories. Taken together, these difficulties suggest that we may not solve the question of what came before the Big Bang anytime soon, and that we may never solve it conclusively. The answer may remain perpetually out of reach. This is a hard thing to accept, especially after a journey like this one. We naturally want to know. We have looked at all these strange and beautiful theories, and we want to be told which one is right. But the honest answer is that we do not yet know, and we may not for a very long time, and it is possible we will never know. This is not a failure of science. It is a recognition of how difficult the question is. We have done remarkable work in even being able to formulate the proposals and explore them. Settling the question may be beyond what science can do in any human time frame, and may, in some cases, be beyond what science can do at all. Even so, we should not let this fact close down our curiosity, because the very act of asking has taught us things we could not have known otherwise, including some genuinely unsettling things about what the Big Bang took from us when it happened. One of the most quietly disturbing aspects of any cyclic or pre-Big Bang cosmology is what it implies about lost information. If something existed before our universe, a previous cosmos, a previous eon, a previous brain configuration, then that something had its own history, it had its own structures, its own arrangements of matter, its own events, and almost all of that history is, in most of the theories we have considered, irrevocably destroyed by the transition that produced our Big Bang. The information is gone. The previous universe, even if it really existed, is in a deep sense unreachable by us. Not just hidden behind a wall, but actually erased. Consider what this means concretely. In the Big Bounce picture, the previous universe was crushed by its own contraction, with its galaxies torn apart, its stars destroyed, its atoms broken down. By the time of the bounce, almost no specific information about that universe remained. Only the most basic coarse properties survived. The total energy, perhaps a few fundamental quantities. Everything else was erased. If life had existed in the previous universe, no record of it survived. If civilizations had built monuments to themselves, those monuments were broken down to particles, and the particles were broken down further, until nothing remained of the original arrangement. The previous universe was, in every meaningful sense, forgotten. The same is true to varying degrees in most of the cyclic theories. The ekpyrotic universe collides with another brain, and the energy of the collision wipes out most of the prior structure. Conformal cyclic cosmology preserves a bit more, perhaps the faint imprints of supermassive black holes, the Hawking points, but the bulk of the previous eon's history is lost. The transitions are not record-preserving. They are erasures. Each universe, when it is born almost fresh with only the faintest traces of what came before, if any traces at all. This is one of the most disturbing things about cyclic cosmology. It is not just that the previous universe existed, it is that the previous universe is gone in the strongest possible sense. Whatever happened there is unrecoverable. Whatever beings might have lived, whatever they thought or felt or built, has been destroyed. The cycle does not preserve history, it eats it. Each cosmic generation rises from the ashes of the previous one, but the previous one is genuinely ashes. Nothing of it is left except the abstract fact that it must have been there. There is a kind of loneliness in this picture, a loneliness that grows the more you think about it. If life arose in the previous universe, and we cannot rule it out, then those lives are now totally inaccessible. Not just to us, but to anything. The information that recorded those lives was crushed in the bounce or burned in the brain collision, or smoothed out in the conformal transition. The beings who experienced those lives have, in every sense that matters, vanished without a trace. They are not even ghosts, they are absences, the empty space where a vanished history used to be. And the same will happen to us. If the cyclic picture is right, then our universe too will eventually end in a transition that erases most of its history. our galaxies, our stars, our worlds, our lives, all of it will be destroyed in the compression or the brane collision or the conformal transition. Whatever we have built, whatever we have learned, whatever stories we have told will be lost. The new universe that arises from our ending will not remember us. It will not even know we existed, except in the abstract sense that something must have preceded it. The total cosmic history is one of endless creation and endless erasure, with each cosmos a brief flicker of structure between two great eras of forgetting. This is one of the more uncomfortable thoughts in modern cosmology, and it is one that is not often emphasized in popular accounts. The cyclic universe is sometimes presented as comforting. The cosmos is eternal, there was always something, there will always be something. But it is comforting only at the level of the cycle itself. At the level of any particular cosmos, any particular set of galaxies and stars and lives, the picture is bleak. Nothing within a single cycle is preserved. Everything is impermanent at the level we actually care about. The eternity of the cycle is bought at the cost of the impermanence of every individual cosmos. There is perhaps one consolation. The information may not be entirely lost. In some quantum theories, information is conserved at the deepest level, even when it appears to be erased in practice. The history of the previous universe in this view is encoded somewhere, in subtle correlations among the particles of our cosmos, in fine details of the cosmic background, in patterns we cannot read but that nonetheless contain in scrambled form the memory of what came before. If this is right, then nothing is truly lost in an absolute sense. It is just made inaccessible. The previous universe is still there, encoded somewhere in ours, even if we can never decode it. Whether this is consolation or further frustration depends on how you feel about a memory that exists but cannot be read. What this whole line of thinking points to is a deeper question about the limits of what we can know, about what science can and cannot reach. We are pushing against the edges of what is observable, what is computable, what is even thinkable. And it is worth pausing to consider before we close what those limits really are, and what it means to live as conscious beings at those very limits. We have reached, in this investigation, the very limit of what science can currently say about the deepest question. We have looked at multiple serious proposals for what came before the Big Bang, and we have seen that none of them is yet proven, that some may never be provable, and that the question itself may in some theories have no meaningful answer. Before we move on to what all this might mean for us, it is worth sitting for a moment with the limit itself, with the boundary of human knowing, and what it means to be a creature who can ask questions that may never have answers. Science has been astonishingly successful across the past several centuries at expanding the range of what humans can know. Questions that for thousands of years were the province of myth and religion, the structure of matter, the origin of species, the age of the earth, the nature of stars, have been brought one by one into the realm of evidence and measurement. We now know with remarkable confidence that the universe is 13.8 billion years old, that the Earth is about 4.5 billion years old, that life evolved on Earth over billions of years, that matter is made of atoms which are made of quarks and electrons. These are not guesses, they are conclusions supported by enormous amounts of evidence, and they have transformed our picture of what we are and where we came from. But there are limits, and the question of what came before the Big Bang sits squarely at one of them. We have pushed our science as far as we can, and we have produced beautiful, intricate, mathematically detailed proposals. We have peered into the cosmic background with extraordinary precision. We have looked for signatures of inflation, of bouncing universes, of eons, of brane collisions. We have done remarkable work, and we have not yet reached an answer, and we may not for a very long time, and we may never reach one at all. This is a humbling thing to acknowledge. Science, for all its power, is not omniscient. There are questions it can ask that it cannot with current tools answer. There are facts about the universe, the very deepest facts, perhaps, that may lie permanently beyond our reach. The conditions of the very early universe are screened by the cosmic background. The structures of any prior universe are erased by the transition that produced ours. The multiverse, if it exists, is unobservable in principle. The quantum gravity we need to describe these regimes is not yet complete. At every turn we run into limits set by the physics of the universe itself, not by failures of imagination or technology. What does it mean to live as a being who can ask questions that may not be answerable? It is in some ways a profound feature of conscious existence. We are creatures who can formulate questions our minds cannot resolve. We can wonder about what came before time, what lies beyond the universe, what it means to be aware at all. These questions arise naturally in any mind capable of reflection, and many of them, perhaps all of the deepest ones, do not have clear answers. They lead us to the edges of our understanding, and there we stand, looking out at a vastness we cannot fully grasp. There is something both painful and ennobling in this position. Painful because we want to know. We are wired to seek answers, to resolve uncertainties, to fit the world into patterns we can understand. The deepest question, what was at the beginning, is one we have asked for as long as we have been able to ask anything. And the honest answer, after all our progress, is still, we do not fully know, and we may never know. That is hard to accept, but it is also ennobling, because the very fact that we can ask the question, that we can develop sophisticated proposals about what might be the answer, that we can map our own ignorance with such precision, this is a remarkable achievement. No other creature on Earth, as far as we know, asks what came before the Big Bang. We are alone on this small planet in being able to formulate the question and to pursue it scientifically. The pursuit itself, even when it does not reach a conclusion, is one of the most extraordinary things our species has ever done. And there is more. The limit of science is not the limit of meaning. Even if we never answer the question of what came before the Big Bang, we have learned, in the process of asking, an enormous amount about the universe. We have refined our theories. We have built tools that have transformed our understanding of cosmology. We have come to see the universe more clearly, even if we cannot see all the way back. The journey of asking is a journey of becoming, of growing in our understanding of ourselves and our place. The answer may be permanently out of reach, but the asking has changed us, and it has been worth it. So we live at a limit, asking questions that may not be answerable, and finding meaning in the asking itself. This is the condition of being conscious in a universe that is far larger and older than ourselves, and far stranger than any simple picture would suggest. The deepest question, the question of beginning, may remain open forever, and we will go on asking it, because that is what minds like ours do. We do not need an answer to be moved by the question. We do not need certainty to be transformed by the pursuit. And the very act of pursuing the question has revealed new tools, new lights, new ways of looking at the sky we always thought we knew. We have spoken several times of the cosmic microwave background, the wall of oldest light, beyond which we cannot directly see. It deserves a closer look here, because it is the most important window we have onto the early universe, and it carries within it almost everything we know about the conditions of cosmic infancy. It also hides almost everything we want to know. The CMB is both a revelation and a frustration, simultaneously the source of our greatest cosmological discoveries and the wall behind which the deepest mysteries hide. The cosmic microwave background was discovered, somewhat by accident, in the 1960s by two radio astronomers, Arno Penzias and Robert Wilson. They were trying to eliminate noise from a radio antenna and could not figure out what was producing a faint uniform signal coming from every direction in the sky. Eventually, in collaboration with cosmologists, they realized they were detecting the afterglow of the early universe, the relic radiation released when the universe was 380,000 years old and atoms first formed. This discovery was one of the most important moments in 20th century cosmology. It confirmed, beyond reasonable doubt, that the universe had a hot, dense early phase, just as the Big Bang theory predicted. In the decades since, the cosmic background has been mapped with extraordinary precision by satellites including COBE, WMAP, and Planck. These missions have produced exquisite maps of the temperature of the early universe, showing tiny variations from place to place, temperature differences of a few parts in 100,000. These variations are the seeds of all the structure we see today. The slightly hotter spots were slightly denser regions, which over billions of years collapsed under gravity to form galaxies and clusters. Everything in the cosmic web, every galaxy, every star, every world, grew from these tiny early variations. What the CMB tells us about the early universe is breathtaking. We can read, from the patterns in the background, the composition of the early cosmos, how much ordinary matter, how much dark matter, how much dark energy. We can read its age, its rate of expansion, the curvature of space. We can read the conditions during inflation, the temperature at which atoms first formed, the size of the observable universe. The CMB is the richest source of cosmological information we have, and it has transformed our understanding of the universe over the past few decades. But for all that the CMB reveals, it also hides. It is the wall beyond which we cannot directly see. The patterns in the background carry imprints of what happened before, during inflation, perhaps before inflation, in whatever state preceded our cosmic era. But these imprints are subtle, mixed, and difficult to read. We can constrain some pre-CMB physics by carefully analysing the patterns, but we cannot directly observe what was happening. The CMB is the closest thing we have to a window into the early universe, but it is a tinted, filtered window. We see shadows of what was, not the thing itself. This is why so much of modern cosmological work focuses on the CMB. To distinguish between inflation and ekpyrotic models, between simple inflation and eternal inflation, between cyclic cosmologies and the no-boundary proposal, for all of these we need finer and finer measurements of the cosmic background. We need to detect not just the temperature variations but the polarization of the microwave light, which carries additional information about what was happening just before the CMB was released. We need to look for tiny patterns that could be the signatures of gravitational waves from the very early universe, which different theories predict with different intensities. Future satellites and ground-based observatories are working on exactly these measurements. They are looking for the faint polarization patterns called B modes, which would be evidence of gravitational waves from inflation. They are looking for non-Gaussian features that might distinguish between different early universe scenarios. They are looking for the Hawking points that Penrose's theory predicts. None of these signals is easy to detect. They are all small, contaminated by foreground sources, and require very careful analysis. But over the coming decades, the precision of CMB measurements will continue to improve, and gradually our ability to discriminate between pre-Big Bang scenarios will improve with it. It is even possible, though by no means certain, that we will someday have direct evidence for one of the theories we have considered. If the Hawking points are real, that would be evidence for conformal cyclic cosmology. If the polarization patterns match the predictions of inflation precisely with no deviation, that would favour inflation over its competitors. If a particular kind of right-handed neutrino is detected by particle physics experiments, that would support the CPT symmetric universe. The CMB and related observations are slowly closing in on the question of what came before, even if we cannot directly see it. So the cosmic microwave background is both our window and our wall. It tells us an enormous amount about the early universe, and it hides almost everything we most want to know. Behind it lies the inflationary epoch, the supposed singularity, and any prior state, multiverse, bounce, eon, brain, no boundary, mirror, or tunneling vacuum, that may have preceded our cosmic era. We cannot see those regions directly, but we can read their fingerprints in the patterns of the background, and the reading is getting better all the time. The question of what came before the Big Bang may yet be answerable, in some form, by the patient work of CMB cosmology, and it may be answerable too by tools the world is only now beginning to wield with confidence. Until recently, the cosmic microwave background was almost the only window we had onto the very early universe, but in the past decade new tools have emerged that may eventually let us see further back. They include gravitational waves and ripples in the fabric of space-time itself, which can carry information from the earliest moments, and powerful computer simulations that let physicists explore conditions no laboratory could ever reproduce. Together, these tools may, in coming decades, transform our ability to test theories of what came before the Big Bang. Gravitational waves were predicted by Einstein in the early 20th century, but they were not directly detected until 2015, when the LIGO observatories caught the signature of two merging black holes a billion light-years away. Since then, gravitational wave astronomy has become a major field, with detectors picking up dozens of events from merging black holes and neutron stars. These detections have been extraordinary in their own right, but they are only the beginning. Future detectors, both on Earth and in space, will be sensitive to gravitational waves from a much wider range of sources, including, potentially, the very early universe itself. The reason gravitational waves are so important for our question is that they can travel through the early universe without being absorbed. Unlike light, which is scattered by the hot dense plasma of the first 380,000 years, gravitational waves pass through it almost unimpeded. This means that gravitational waves generated in the very early universe, during inflation or in any earlier process, could still be reaching us today, carrying information from a time before the CMB. If we can detect these primordial gravitational waves, we will have a direct window into the early universe that goes beyond the CMB barrier. Different theories of the early universe predict different gravitational wave signatures. Inflation typically predicts a particular spectrum of gravitational waves with a certain amplitude. Ekpyrotic models predict a different, generally much smaller signal. Some bounce models predict their own characteristic patterns. The CPT symmetric universe makes its own predictions by measuring the spectrum of primordial gravitational waves, even just establishing whether they exist at the predicted levels. We could distinguish between these scenarios. The space-based detector LISA planned for the 2030s is one of the missions that may help us do this. Earth-based experiments looking for polarization patterns in the CMB, which can be caused by primordial gravitational waves, are another approach. The other major new tool is numerical relativity, the use of powerful computers to simulate the equations of general relativity in regimes where they cannot be solved by hand. In the past, physicists could only treat the very early universe with approximations and simplifying assumptions. Now, with modern supercomputers, they can simulate the full equations in extreme conditions. This is particularly important for understanding what happens at or near the supposed singularity, where the equations are most complex. Numerical relativity is being used in recent work by cosmologists including Eugene Lim, Katie Clough, and Josu Orokwetsia to explore scenarios where simple analytic approaches fail. These simulations are still in their early stages, but they are beginning to make real progress. They can model the transition from a contracting universe to an expanding one in bounce cosmologies. They can simulate the dynamics of inflation in more detail than ever before. They can explore what happens when different regions of an inflating universe end inflation at different times. In a recent paper from 2025, this research program was laid out explicitly. Numerical relativity, the authors argue, is the right tool for probing what may have come before the Big Bang, and it can be applied to test the predictions of string theory, cyclic models, and other competing pictures. The combination of these tools, gravitational wave observations, more precise CMB measurements, and numerical relativity simulations, is making the question of pre-Big Bang physics more tractable than it has ever been. We are not at the point of answering the question definitively, but we are no longer just speculating. We have specific theories with specific predictions, and we are slowly building the tools to test those predictions. The next several decades may bring real observational discrimination between some of the candidates, even if the deepest question, what truly came before, remains stubbornly out of reach. What is striking when you consider this development is how the question of cosmic origins has evolved over the course of a single lifetime. A few decades ago, asking what came before the Big Bang was considered almost metaphysical, beyond the reach of science. Now we have multiple competing scientific theories, observational signatures for at least some of them, and rapidly improving tools to test them. The question is not yet answered, but it has been transformed from an unanswerable speculation into a serious scientific problem with active research and real possibility of progress. That transformation is, in itself, one of the great achievements of modern science. And yet, even as we develop these tools, the underlying strangeness of the question remains. Whatever we find, Sabun, whatever theory the data eventually selects, if any, will not be a comfortable answer. Each of the candidates we have considered is disturbing in its own way. The universe, however it began, did not begin in a way that conforms to common sense, and what it means to live in a cosmos with such a strange origin, and possibly such a strange continuation, is the final thing we have to think about before this journey ends. We have explored a series of theories that suggest, in different ways, that our universe is older than the Big Bang, that something existed before, or that there was no before because the very concept does not apply, or that we are one in an infinite chain or array of cosmoses. Whichever picture turns out to be right, we live, in a profound sense, in a universe that is far stranger than the simple Big Bang story suggested. And it is worth taking a moment, before we close, to think about what it is like to live in such a universe, to be a conscious being in a cosmos whose origin is genuinely beyond our comprehension. Consider what it means to know, or even to seriously suspect, that the universe did not begin at the Big Bang. For most of human history, the question of origins was the province of myth and religion. People told stories, creation stories, to give themselves a sense of where they came from. These stories were comforting in their own way, even when they were dark. They placed humans in a framework, with a beginning and a meaning, and they gave the cosmos a shape that minds could hold. The Big Bang Theory, when it first emerged, was a kind of secular creation story. The universe began 13.8 billion years ago, in a great event, and from there everything followed. But now we are being told that even this story is too simple. The Big Bang may not have been a true beginning. There may have been something before, or there may have been no before at all. The universe may be eternal in some larger sense, or it may have arisen from quantum nothing, or it may be one of an infinite ensemble. The simple story of creation has dissolved into a set of competing, complex, strange proposals, none of which conforms to common sense and none of which is yet confirmed. We have lost the comfortable narrative without yet gaining a clear replacement. This is a peculiar position to be in. We know more about cosmology than any humans before us. We have telescopes and satellites and supercomputers. We can map the cosmic background with extraordinary precision. We can detect gravitational waves from the collisions of black holes a billion light years away. We have powerful mathematical theories and exquisite observational tools. And yet, when we ask the simplest, deepest question, where did it all come from? We find ourselves staring at a wall of beautiful, disturbing, unconfirmed proposals, none of which we can be sure is right. What is it like to live as a being in such a universe? In some ways, it is humbling. We are not at the center of anything. We are not in a cosmos with a clear story. We are in a universe whose origins are genuinely beyond our current understanding and may always be. Our place in things is far stranger than we thought. The simple picture of being born into a cosmos that began 13 billion years ago has been replaced by something more elusive, being conscious in a cosmos that may have always existed, or that arose from nothing, or that is one of countless others, and we cannot say which. But it is also, in its way, magnificent. We are creatures who can ask these questions. We can hold the possibilities in our minds. We can develop the mathematics, refine the theories, build the instruments. We are, despite our smallness, capable of confronting the deepest mystery there is, and of making progress on it, even if we cannot yet solve it. Our position at the edge of knowing is the position from which we can reach toward what is beyond knowing. That is not nothing, and there is something else. The fact that the universe may be older than time, or eternally cycling, or one of a many, does not change what is in front of us right now. Whatever the deep origin of the cosmos turns out to be, we still live in it, in this small corner, with this small life, with the people and places and moments that fill our days. The deep cosmology does not diminish the immediate. If anything, it heightens it. The improbability of our being here, in a universe of such strangeness, is overwhelming. We are conscious beings, briefly aware, in a cosmos that may be far stranger than any simple story would suggest. That is a remarkable thing to be. So living in a universe that may be older than time, or that arose from nothing, or that is one of many, is in the end not so different from living in any other kind of universe. We still have our days, we still have our connections, we still have the brief, bright awareness of being here at all. The cosmic strangeness is the backdrop, not the foreground. And the foreground, the small bright life in front of you right now, is, in its own way, as remarkable as anything in any of the theories we have considered. It is, perhaps, the only thing we can really know, and the only thing we will ever really have. Holding both at once, the cosmic and the immediate, may be the deepest practice the question of origins has to offer us, because the part of all this that is genuinely disturbing, and the part that turns out to be unexpectedly beautiful, are both worth facing directly before we end. Throughout this journey, we have been honest about the disturbing aspects of each theory we have considered. The eternal multiverse with its infinite copies of you, the big bounce that crushes the previous universe almost out of existence, the eons that fade into each other, leaving only faint scars, the no-boundary proposal that says before is malformed, the mirror universe running backwards on the other side of the Big Bang, the brain collisions that cycle forever, the quantum tunneling from a structured nothing. Each of these has an unsettling edge. None of them allows the universe to be a simple thing. Let us name the disturbance directly, because it is worth seeing all at once. In every one of these pictures, the human position is more precarious than the simple Big Bang story suggested. We are not the center. We are not unique. Our universe is not the only one, or it is the latest in an infinite chain, or it has a mirror twin we cannot reach. The history of our cosmos may be one of many that were erased, will be erased, or were never really original to begin with. Our deepest question may not have a meaningful answer at all. The structure of reality, when probed at its origin, dissolves into possibilities that all unsettle the ordinary picture in some way. And there is more. In an infinite multiverse, your life is not unique. Some other version of you is living some other version of your life, infinitely many times, in places you cannot reach. In a cyclic cosmos, your universe will eventually end and almost everything you know will be erased. In Penrose's Eons, you are one chapter in an unending book whose previous chapters are nearly gone. In the no-boundary picture, the very concept of an origin is dissolved. None of these stories preserves the simple human sense that we are at the start of something in something with a clear past and a meaningful place. The cosmic narrative we want to tell about ourselves does not survive contact with the actual physics in any of the variants on offer. This is the disturbing part. We have to face it honestly. Modern cosmology, when it takes the question of origin seriously, finds itself proposing pictures that no human mind would have invented out of comfort. The pictures are mathematically beautiful but emotionally cold. They do not flatter us. They do not place us at the center of anything. They do not promise that anything we have built will endure. They are by every measure more disorienting than the simple stories of beginning that humans have told themselves throughout history. Science has not given us a more comforting creation myth. It has dissolved the very idea of creation and given us, in its place, a set of strange, demanding possibilities. And yet, and here is the turn, there is also something profoundly beautiful in this. We must hold both at once. The disturbance is real. The beauty is also real. They are not separate. They are two sides of the same recognition. The beauty is this. We are creatures capable of asking these questions and following them honestly, even when the answers disturb us. We did not flinch from the multiverse, the bounce, the eon, the void. We did the math, we ran the simulations, we looked at the data, and we let the universe be as strange as it turned out to be. We did not insist on comforting stories. We let go of our simpler creation myths and replaced them with these stranger, harder ones, because the harder ones are more likely to be true. That willingness to let the universe be what it is, even when what it is unsettles us, is one of the most remarkable things our species has ever done. The beauty is also in the very strangeness itself. The universe, it turns out, is far richer, far more layered, far more imaginative than any simple story. It may be eternal, or it may arise from nothing, or it may be one of an infinite ensemble. It may have aeons, or brains, or mirrors. It may have copies of you scattered through space we cannot reach. None of this is comforting, but all of it is astonishing. We live in a cosmos whose deepest structure is more inventive than any story we could have made up. Reality is, by every measure, stranger than fiction. And that in itself is a kind of gift, even when the gift is uncomfortable to receive. And finally, the beauty is in the place we hold within it. Whatever the universe turns out to be, we are the part of it that wondered and asked and reached. We are the small, fragile awareness that took on the question of cosmic origins and made progress, even where progress is hardest. The galaxies do not know they came from anywhere. The stars do not wonder what was before. Only minds like ours can do that. And we did it, with mathematics and telescopes and patience. The very fact that we are disturbed by what we found is a measure of how far we reached. A creature that did not understand would not be unsettled. We are unsettled because we understand at least in part, and that understanding is a kind of triumph even when it makes us small. So the disturbing part and the beautiful part are inseparable. The universe at its origin is far stranger than we hoped, and we, in confronting that strangeness, are far more remarkable than we knew. Hold both. Neither cancels the other. The strange cosmos is real, and so is the small bright mind that has come to know it. Together they are the picture, the whole picture, of what it means to live at the edge of the deepest question, small, fragile, mortal, and yet somehow awake. We have come to the end. We have looked at 7 major proposals for what came before the Big Bang, and we have faced their disturbing implications, and we have acknowledged that we may never know which is right. Now, at the close of the journey, let us stand for a moment at the edge of the question itself and feel what it is to be here, on this small world, at the edge of the deepest mystery we have ever asked about. Consider where we are. We are on a small planet, in a thin layer of atmosphere, on a rocky world circling an ordinary star. The star is one of 400 billion in our galaxy, and our galaxy is one of 2 trillion in the observable universe. The observable universe is itself, in many of the theories we have considered, only a small region of a far larger whole, a single bubble in a multiverse, or one eon in an infinite sequence, or one face of a mirror, or one cycle in an endless chain. And the very origin of all of this, the Big Bang, the supposed beginning, may not have been a beginning at all, but a transition, a continuation, a quantum fluctuation from a state we cannot fully describe. This is the situation. This is where we sit. We are small beings in a small place asking the largest question there is. We have done our best with the tools we have. We have produced mathematics of staggering depth and beauty. We have built telescopes that can see almost to the wall of oldest light. We have looked for the signatures of inflation, of bouncing universes, of conformal eons, of brain collisions. We have done remarkable work, and at the end of all that work we still do not know what came before the Big Bang. We have a set of beautiful, disturbing, unconfirmed possibilities, and we do not yet know which is right, and we may never know. There is something both crushing and ennobling in this. Crushing because we want to know. We are minds wired to seek answers, and the deepest question, the question of origins, is one we cannot yet resolve. Ennobling because the very fact of having reached this point, of having transformed the question from unanswerable speculation into serious scientific inquiry, is one of the most extraordinary things our species has ever done. We are at a frontier that no creature on Earth has ever before been at, and we are standing there as far as we can stand, looking out at a vastness we cannot fully see. What is on the other side of the Big Bang? We do not know. It may be an infinite multiverse. It may be a previous universe that was crushed into ours. It may be a previous aeon whose ashes we still carry faintly in the patterns of the cosmic background. It may be a mirror cosmos running backwards. It may be a brain collision in a higher dimension. It may be a quantum tunneling event from a state without space or time. It may be nothing at all, not as an absence, but as a malformed question that has no meaningful answer. We do not know, and the most honest answer we can give after everything is, we do not know, and we are working on it, and the work is one of the most beautiful and difficult things humans have ever done. So here we stand there, at the edge of the first moment, looking out at a question we cannot answer, and here is the thing to hold on to. The not knowing is not a failure. It is a sign of how far we have reached. To stand at the edge of the deepest question is to stand at the limit of what minds can do. We have come as far as anyone has ever come. The question of what was before the beginning is the question we have inherited as a species, and we have made more progress on it than any generation before ours. We may not solve it, but we have approached it as honestly and carefully as anyone could. And there is one more thing. Whatever the answer turns out to be, whatever lies beyond the Big Bang, we are here. We are conscious. We are wondering. We are looking up at the sky and asking the deepest question there is. That is, in itself, a remarkable thing to be. The galaxies do not wonder, the stars do not ask. Only we, the small bright minds in this small corner of the cosmos, take on the question and try to answer it. Whatever we find or fail to find, the fact that we asked is a kind of meaning in itself. The universe, in us, is wondering about its own origin. The cosmos, through human minds, is asking where it came from. That has never happened before, as far as we know. And it is happening now, in you, as you sit and listen and wonder, along with the long chain of minds that has wondered before. So when you go outside tonight and look up at the stars, hold this in mind. The light you see is old, older than the earth, older than the sun. And behind that old light, behind the cosmic background that screens the early universe, lies a region we cannot directly see, where the deepest question of all hides its answer. There may have been a previous universe, there may have been an eon, a brain, a mirror, a fluctuation, or no before at all. We do not know, but we are asking. We are the universe asking, and we will go on asking as long as there are minds to ask. That perhaps is enough for tonight, or